Looks like we are live. Okay, so Elon Musk is now firmly in the driver's seat for the next book, as he calls it, not chapter, but book of Tesla's evolution, from autonomous cars and the Robotaxi network to Optimus and advanced AI chips, even data centers in space, bases on the moon and Mars. The Muskonomy is going to stretch across the solar system. The age of sustainable abundance is here, and I've got a star panel of experts for you to break it down, this incredible future that we're racing towards in alphabetical order. Brian Wong, expert deep tech analyst, investor, and futurist thought leader. Chris Starson, CEO of Digital Habitats Corporation. Gustav Anderson, hand surgeon and professor of anatomy at the University of Umeå in northern Sweden. We're hoping John Gibbs, Dr. Know-it-all, will join us in a bit. I believe he's currently flying up there somewhere, so hopefully when he lands...
His head is literally in the clouds.
In the clouds, yes. Marshall Jim is hyperscaler and data center specialist. He's focused on energy systems, automation, and sustainability. Mehrdad Farimani, he's been designing humanoids and other types of robots for over 10 years now. And of course, Scott Walter, mechanical and aerospace engineer and humanoid bot sensei to the internet. Welcome, gentlemen. It's great to have you all with me. We've got a lot to discuss.
I feel like Paul Lynn here on Hollywood Squares. I'm in the center.
Well, you ought to be. You're normally the focus of everyone's attention. So don't be surprised. All right, so here's a little bit of a quick note to our viewers. We're live across YouTube, X, and LinkedIn. So keep your questions ready, and we'll try and get to as many of them as we can once we do finally open up to audience questions. We're also streaming on Brian's channels. So thank you, Brian, for that. Let's now begin with a quick round around the panel. What do you make of this age of sustainable abundance that Elon is promising? Shall we go in alphabetical order? Let's start off with Brian.
Well, there was huge announcements that he made yesterday, talking about needing so many chips, he'll need a terafab, which involves like 10 lines, each making 100,000 wafers per month. Obviously, you start with one line and scale to the 10. Each one would cost on the order of $10 to $20 billion each. And if he was lucky, he could complete one in 2 years. Probably would happen after the scaling of the Samsung facility in Texas, where he's closely working with them. But the end point of that is more insane than and more amazing than most people realize, because typically you have about 100 chips per wafer, depending on the size of your chip. If you have a really big chip, you might have 50, like the B200 or something like that. So the end point of 1 million wafers per month is basically 1 billion chips per year. And 1 billion chips per year, each using about 1 kilowatt, is a terawatt of power. So that's terawatt power per year. So this is huge growth, and something I'll discuss with a short presentation I have later is how those things kind of pencil out in terms of like how you do it, and the ultimate thing of like how do you power all the things. That's what he's doing, the AI space. So it's like the vision he has is really, really grandiose, beyond what even people who are kind of like listening, kind of like it flew by them, like how amazing it was. When you run the numbers on it, it just goes really crazy. So
it is crazy, and I'm hoping Marshall will shed some more light on the energy problems that we're facing with scaling AI in a bit. But Chris, you're next. What's your big takeaway?
I'm extremely encouraged as a person who spends his time looking at the singularity, figuring out how we can accelerate it. I'm very encouraged that we are seeing this plan evolve, because people like Diamandis and Kurzweil and others have discussed for some time this is a possibility. And the encouragement comes that there's a real world company that's bringing out real products that look like they may ultimately be the prime agent of change for taking life on this planet and evolving it to a Kardashev 2 civilization. So that's exceptionally encouraging.
Yeah, it is. All right, so since we're going in alphabetical order, Gustav, the hand surgeon and
Yeah.
Mr. Scissors, where are your props? Let's see the hand.
I got my hands ready to go. So yeah, he was in a good mood yesterday, as one would expect, given the vote, the
Yeah,
outcome of the vote, and
you would expect, yes, hopefully.
and I mean I think it's like really trying to fight the good fight for capitalism, if you so will. I mean, if they manage with the plans and deploying this age of abundance, it will benefit all of us in the end. It's not just Elon getting $1 trillion, which the media will have you think. So yeah, it was a really nice presentation. I sadly had hoped we never get any new stuff, very seldom, but I had hoped we would get some new stuff on the bot, and perhaps the Roadster could fly in from the sides or whatever. But
That would be cool.
We'll have to wait till April Fools.
Yeah, we will have to wait indeed. All right. Marshall, your takeaway.
My takeaway is there's simply not enough electrons on planet Earth. But I do like what Elon said, right? Is that the big fireball in the sky, right? Trying to build fusion reactors or whatnot. Well, how about just harness the energy of the sun? I mean, StarCloud's already doing it, right? They got an AHB 100 in orbit using solar panels, and on top of that, not just the energy, right? To build gigawatt facilities, you literally need 10 electricians per megawatt to build them. So I don't think there's enough electrician and skilled trades in general to build all this. It doesn't matter if you put it in space, under ocean, or on the ground, or wherever, or even Mars, right? So it's very exciting, really very exciting.
Yeah. I think those chips and energy, two of the biggest problems, really. Merdan, you're next. And I got to say that, here on Over the Horizon, I try and keep it grounded, and we take in all sorts of views. And I think it's important to stay grounded, to stay skeptical of a lot of the hype, because the reality is very different. And I'm hoping I can lean on you, Mehrdad, to keep us grounded.
Oh my God, I have heavy loads on my shoulder now. But and probably a lot of people would hate me after this session, right? A lot of Tesla shareholders. But to be frank, first, I didn't really watch the full demo or whatever we can call it yesterday. I watched some recaps after you told me, and I've been reflecting on it because at the same time, a friend of mine sent me a few funny videos from the DARPA robotics challenge, if you remember, something around 10, 12 years ago. I've been thinking, okay, what have we been thinking about the development of humanoids and what has happened so far? And yeah, I'll try to talk about it later. But overall, a man with big dreams. We shouldn't underestimate him. But I don't know. It's maybe not about a certain company or a certain person. It's about where humanoids are, how capable they are, and what is actually achievable with today's technology. So yeah, that's my take so far.
Yeah, I think that's fair, because there are problems. They're not insurmountable. The physics of the universe doesn't kind of defy any possible solutions coming up on the horizon. It's just a matter of engineering and how much of A, money, and B, effort you put into it, right? So, well, where do we begin? We've got so much to talk about, from bots to autonomous cars to Robotaxi.
You didn't get Scott
Orbital
Walter
AI.
to do his.
Yeah, all right.
You need
So let me
Scott.
just quickly load up Scott's slide.
Oh, wait! Before you go, I thought we were just doing a quick recap first before we go there.
Okay.
And the other thing is, like, I thought R comes before S written, so you go.
Okay, so my big takeaway was I was kind of it was a bit of a dampener for me, because, like Gustav, I kind of expected a little more. I was really encouraged to hear Elon talk about terafabs, because energy and chips are the two big problems, and it's pretty clear that He's been thinking a lot. The fact that he's talking about building a terafab is really encouraging, because that's a limiting factor for intelligence and artificial intelligence. And given the geopolitics of the world that we live in, it's really important for Tesla to be vertically integrated, but also to be independent and have most of its, let's say, supply chains on American soil or on friendly shores. So the news about the terafab was really encouraging. Moonbase Alpha, quite a bit of a surprise. Of course, this was pre-shareholder meeting, but it's good to see that. I think we all have a debt of gratitude to pay to Sean Duffy. He seems to have, rubbed Elon the wrong way enough to respond and take action. And Moonbase Alpha is going to be really interesting, because I've always believed that the moon is a viable stepping stone to Mars and the solar system and the space economy, whether it's in orbit or in space. So energy, of course, we know that Tesla has done a lot, especially with the mega blocks, and Chris and I have talked in detail about the mega blocks here on Over the Horizon. So energy and chips and data gathering, I think we're on the right path. I'm happy Elon is locked in for the road to 8.5 trillion. I think my bet is we're going to have another compensation plan, maybe around 2030, 2031, as Brian and I have discussed. So I think it's a green signal, it's a green light, and it's time to get excited, but also time to stay realistic. Over to you, Scott.
Okay, well, everyone stole all my thunder, so I don't have anything left, especially Gustav. So I guess the main thing is, if you had never seen a shareholder meeting, it would have been pretty interesting, but it was mostly Elon's greatest hits on everything. The only thing that was like new for me was like when you mentioned the terafab, and then I'm just like, seriously, I know people have kind of brought this up, but that is like quite the undertaking. And all I had to do is like, Anastasia in Tech, she's done a couple of videos recently talking about the 2 chip fabs in Arizona and in Texas. And after you do that, man, that would talk me out of even considering the idea of making that. But then again, Elon thinks very big. But just kind of going back to everything was about sustainable abundance. And, abundance means a lot of things. But in the end of the day, it means about moving atoms around, reconfiguring them to build stuff. So you need something there. That's the hard part. You need all these other things. You need energy, and you need compute, which all have to get solved. And then you need the robotics. And unfortunately, we didn't get much of a robotics update. I mean, there was really nothing there. We were expecting a little bit more. I thought there would be more optimized there, maybe doing other things, at least handing out popcorn or doing something like that. I was not expecting anything with a V3 reveal. But yeah, so everything we got was basically information we've already known. And it just means they're being a little bit wiser this time on how much they telegraph to everyone in advance. But still, if we want, we can do a retrospective and kind of take a look at where the designs are now and then when it's appropriate. So those, and then the exciting part, I think, for me is that I'm also a space geek. So when people start talking about all these big structures in space, and I've been staying on the sidelines watching the debate on X about that, where there's a lot of people who are excited about it. And then you get the next group of people that come in there and they're the wet rags, and they want to throw water on it. They're the skunk at the picnic, whatever you want to say. So and I'm looking at that, and you probably see all those memes. You know that one with Matt Damon where he's sitting there explaining to someone why he doesn't know what he's talking about, kind of thing. So everyone's doing that, and it looks like they're all using ChatGPT to help refine their argument, which always ends up being 3 pages of why you can't do it and why you don't know what you're talking about. And I'm going through and looking at all these things, and I'm saying, okay, is everything I'm seeing on here, are these reasons or are they excuses? And so everyone's saying, well, you don't realize, dissipating heat in space is like a really hard problem. And you don't know, and then like vibration to the systems and stuff like that. And so you can use that as like your argument, and that's your excuse on why you don't pursue it. Or you just say, that's an engineering problem. And not only that, it's an engineering opportunity, because a lot of people will say, well, we don't know how to get air dampening, and we have to put all sorts of things in there. And I'm saying, you know what? Maybe that's an opportunity, because the vibration that's going on there basically means you get some sort of energy. And maybe you can figure out how to capture that energy as mechanical energy in some useful way to, like, I don't know, maybe pump your cooling fluid around. So this is how aerospace worked, is that every part is expected to do 2 or 3 things. You never design a part for a single purpose. It's supposed to have multiple purposes. And if you bring that mentality to the whole thing, I think your solutions are, well, we get this problem over here. Oh, guess what? By the way, we can take that solution that helps us out over here on something else. So, that's where I am. And so hopefully today, when we get in that discussion, the energy, we can do that. But you're the MC here, Royden. You decide when it's appropriate to start talking hands.
We should start talking hands because we've seen some impressive, shall I say, interesting engineering around the Optimus hand. You've got a few slides for those. Let me just pull them up, and if you can just take us through what you have.
Oh, okay. So
you have control.
Yeah, I guess I have control. I don't know if we'll have to figure out how the clicking is going to work here to advance the next one. So I've got a bunch of slides. They're not necessarily in the order I want yet. So I'll probably be jumping around. I'm getting a bit close. But I put this post, as you can see, that literally was my time. All at 2:37 a.m. Last night. That's what happens when you consume too much Dubai chocolate. And everyone's probably wondering what this cryptic post is all about, and I'll get to it. So this is the teaser to make everyone stick around on exactly what I'm trying to say there. No, I'm not trying to say barf 3 times, even though it looks like that. So somewhere in here, I've got to go ahead and find that. I believe I can go ahead. Yes, there we go. So as you may know, the Optimus hand was on display for those who were attending the shareholder meeting. We did not see actually anything on the live stream, as far as I know. Maybe it was off in a glimpse, but there was no close-ups. And so these are the sources that I'm relying on. I think there was maybe a half dozen people who did it. I saw Herbert there in the live stream, as we all saw Herbert. And I texted him multiple times, but he was like too busy to reply. And I was trying to get him to do something. And I even asked Jeff Lutz, who was there, and at least Jeff had the courtesy to reply back when I was there. But no, Herbert was too good for us. So anyway, trying to give them like some coaching on what I wanted to see, because I think there was like already one hand video out there. So I am relying on these 3 different sources there. Gustav, you can probably pronounce the first person's name better than I can. Is that Torkild?
Torkild, I would say. It's probably it's not Swedish, more Danish or Norwegian.
Okay. So Scandinavian, whatever. So you'll be able to do that. And so I'm using them kind of as a source for some of the breakdowns we're going to do here to get an idea. So this is the second generation of what we saw a year ago. So a year ago at the 1010 Wii event, this is the prototype hand that was on display. And there was a couple of videos on it, and I ended up doing some kind of breakdowns on it. So we can notice a lot of things on here is that it's not refined yet, but we get an idea of the degrees of freedom they wanted to get. And you can see that the tendons that they're using here are clearly sheath tendons, because you notice that they have a curvature in there. If you didn't have a sheath in there, those would be straight lines between the different corners. So we can see that's what's being done. We're going to see there's a little bit difference now. This is like another view that Dirty Tesla was able to get. And from that, I was able to, at some point here, if I can figure out how to advance to the next slide. And from there is to actually show us what all the degrees of freedom, because everyone was saying it's 24 degrees of freedom. Where are those degrees of freedom coming from? So this was like annotating it to get an idea of exactly where they are. And we have some sort of ideas, and with a little bit of guesses down here on the CMC joint for the thumb, because that's the only way you can get to the 22 DOF. The other big question was like, well, how many actuators are there going to be in there? Because something has to be pulling on these puppet strings. And it looked like they were linear drives. We've been able to confirm now that they're definitely linear drives. The question is, how many bundles are there? And there was a lot of bundles. And I speculated in order to get all the movement that you need, you would need to have 24 actuators to be able to do that. And I speculated there's probably 3 rings of 8 or something like that. Turns out I'm wrong. Okay, so we're gonna find out that. So from that, we could clearly see in there that they have these 2 tendons which act for ab and adduction. That allows your fingers to splay back and forth. And also there was a built-in flexure. And then on the next slide here, we're seeing, which is allegedly an extensor, okay? Update on that. So when you start counting all these things, you're really convinced that we need to have there's going to be 24 puppet strings to be able for this 22 doll thing. So it means you're going to need something on the side to be able to. And here's like another kind of view again, looking at that to try to count. And it was just such a jumble. If you try counting there, you can get up to around 16 or 17, but it's really hard to get to 24. But then again, you can say, yeah, but I can't see them all. That's why. So it's very, very hard to tell. So that is the state of about a year ago. Actually, probably longer than that, because this was a prototype that was probably from the previous spring. And then they were allowed to bring this to the event because they didn't need it anymore. Because less than like 4 or 5 weeks later, almost exactly a year to now, we then saw the first attempt to putting the hand onto Optimus. And you can see it's more compact than the original one. The whole forearm, despite the fact that they shoved in a lot of actuators there and was a very human-like hand, and we could see he was able to do the grab. So I think everyone remembers that. Unfortunately, that's like the last update that we ever got of that hand on Optimus. We've never really seen it do anything since then. The other teases we had, this goes back to May, is, as you referred to, Secretary Duffy was visiting Giga Texas, and this hand just happened to show up in the video, despite the fact that people were trying to hide it. Now, my recollection was, and again, this goes back to the Mandela effect, I thought that both hands were covered with a glove, and it turns out, retrospectively, only one of them was wearing the glove, and that's the first time we actually got to see something. So Tesla is finally taking the gloves off here. But it was not zoomed in enough for us to really get an idea of how the mechanism works. So that's sort of the best we've been able to see up to this date. And again, clearly they wouldn't show us anything of what was going on in the forearm. So we had absolutely no idea what was going on. This is the closest we got to that. You might remember around the same time, there was the Q1 update, and the Optimus pilot line was shown to us. And if we zoom in a little bit, we can see, guess what? We can see them actually installing the forearm onto the hand. And let me go back to that. But basically, we couldn't see a whole lot of detail in there. So, I mean, we can see, there's some nice colors in there, but that's about it. It's hard to count what's going on. We're not actually seeing the hand. Yesterday, we finally got the full video of probably what was taken back in the springtime. When they took this shot, probably the same things that were going on. And so now I'm going to ask our illustrious panel a question here. We are looking at this hand being assembled, and I want to contrast what we are seeing here versus what we are seeing here. And you tell me what's different about it.
Okay, so who's going to go first? Let's get the good doctor first, Gustav. Since you're the hand surgeon, and
I didn't really see that much difference, to be honest. But maybe some of the.
I thought there was more stuff in the forearm and in the just beyond the wrist.
It's mechanically the same. Let's say, is there an electrician in the room? Is there someone who does wiring?
I do.
Yes. Okay. So again, looking at what's the difference between the two?
Yeah, other than the red and blue wires, mechanically it looks almost identical.
Yes. So the thing is, this was the early pilot run that went down there, and all the tendons are the same color. And they quickly realized that the tendons were getting crossed, just like an electrician. It's like you start running wires through stuff like that, you want to have them color coded so that you connect them to the right thing. Right. So they quickly discovered, oh my God, everything is getting jumbled here. We're not doing it right. So they decided to go ahead and start color coding these things. So that's the first thing that we can kind of see. And this is an important key to my sort of being able to finally figure it out, because I was focused too much on trying to count the actuators, realizing that this color coding that they finally came up with actually helped me out quite a bit. Mm-hmm. So I'm not going to give everything away, but looking at this, I'm not 100% sure that those are necessarily tendons we're seeing coming on out there, or those might actually be wires. Because if we kind of go back to this picture here, what do you kind of notice about the hand itself?
I also see it color coded, right?
Well,
like the thumb is blue, and then the palm is kind of a cyan.
That looks like it's the cyan stuff. I think it's all tactile sensors. That's all the sensing. And what the sensors need?
Wires.
So we see wires here. And I think if you look at one of these images here, you'll see there is a big ass wire coming on in on up here.
Right.
Now, the other thing is I could only start getting to this late last night, and I'm going through there. And if you actually look at the videos of this going around, you notice there's like lots of blinking lights. And I just assumed that those were lights that are around there. They had all this disco lighting and stuff like that. And I was literally seeing doubles and reflections of stuff that it was a really hard time for me to figure out what was going on until I realized, wait a minute, the lights are literally coming from inside the house. That green flash that you see on there on that thumb, that's not some external strobe light or laser going around or something like that. No, that's actually a LED in there. And so there's also some red blinking lights, and they're all over the hand. So when the hand is moving around, you're seeing all this stuff. And I'm like, what the heck? What? I mean, usually when you start seeing those things, like on motors and stuff, there's like a control board or something like that nearby. And the whole idea of the tendons is that like there's not any electronics in there except for the touch sensing. Unless they also have encoders or something else. So I'm really surprised to see that there were so many LEDs throughout there, flashing and doing other stuff for status report. I don't see what the advantage of that is, except it's more carried mass, more things to break and everything else. And maybe someone who is a double E can inform me a little bit more. But, I thought from here on up, it's a mechanical problem. And all that double E stuff is down here. So what the heck is it doing on up there?
Yeah, it could be feedback, right? So that the green LEDs respond to the green wires and so on and so forth. Yeah. And it's right now it's in they're still in the prototyping phases, right? So they want that feedback of that tech, whatever that sensor is actually working, right?
Yes.
So it gives you visual, because otherwise you don't know, right?
Yeah, they have no idea, because otherwise you're measuring the encoders down here in the forearm.
Right.
And you're trying to figure out the angles up there. And so it could be exactly that. So there's more juice, because when I'm looking at that wire, it's like, wow, there's a lot more going up there than I expected.
Right.
I was almost wondering whether
Scott, can you just go back to the previous slide? Because if you look at the palm
I changed the palm a little bit.
So I see a little indentation there. A bit of a bend. And that's
I know Gustav's got all excited about that. Go with it.
So when I saw it first, I thought, maybe they moved the joint a little bit. So I always been I'm happy that they added the joint for the fifth metacarpal, but it's too far out. It's too distal towards the finger compared to us humans. It should be down here. But and then when I saw this first yesterday, I was like, oh, they actually moved it a little bit, but I don't think they did. It's just that the curvature of the palm now is kind of
it's no longer flat
with my head. And there's some other shapes to it.
So they changed it a little bit. So if
they kind of realized it helps to catch stuff if you have that indentation. I think.
Cool stuff.
So the tennis ball grip.
Yeah.
Interesting.
It doesn't hurt. And if you look at your palm, it might be a little bit hard to see mine right now. I know Gustav is really good at that. Is we can flatten our palms a lot, but I can also go around like that, and it really cups quite a bit. So you can deform your palm a lot more. And none of the robots really can have deformable palms yet, short of like that fifth metacarpal, which is basically what Gustav is saying is like the pinky, the bone that connects the pinky to your palm over here. That's the fifth metacarpal. Is that can kind of come in.
Can you go to the next slide, please, which is a closer view of this?
I think this one here. Right. Yeah, that's the better one.
Bend here. Now, the reason we can bend our palms is because our fingers literally extend into our palm. Vertically, there's a fold.
It's because we're not made out of metal.
Yeah, exactly.
So this joint is not
a joint. A joint there.
Yeah.
Or is that?
I think it feels like it's stiff material. And I mean, they have the MP joint, as we call it, this first joint where the finger starts. They have it a little bit further out to kind of match what we look like. But as you say, this is not a joint. The joint is down there where we bend the finger. So this is just a crease of the skin.
Yes.
So they kind of adapt. And almost all the robotic hands have this kind of fault.
And we're about to get into that. Yep.
But no, I got really excited. Oh yeah, they're showing something new. But then I'm like, no, it's just the same old. Aside from some colors.
Very quickly, Meherdat, any views so far?
I just was thinking about one of the early slides Scott showed about the analysis of the degrees of freedom, and I think actually the DIP and PIP are actually dependent, so they are not.
Yes. So let's be careful about what we mean by degrees of freedom and what we mean by joints.
Right.
So the proper terminology, and unfortunately, the terminology has been corrupted. That everyone has been using degrees of freedom when they really mean joints, because it's a great way of obfuscating everything and not really telling you how many actuators you have. So the current hand, it has 11 joints, but 6 actuators. So it's really a 6-DOF hand with 11 joints. That should be the proper terminology. I'm glad you kind of called me out on that, but I was just trying to like stick to the terms that they were using. I notice right now they call it the V2 hand. It's almost like they're kind of getting away from that terminology. I think we almost have to start talking about degrees of control, since degrees of freedom has lost its meaning, has literally lost its meaning, just like the term literally has literally lost its meaning. Yeah. So maybe we should say degrees of control, something like
True.
that. Yeah.
The second point I wanted to say,
Yeah.
I'm sorry, Gustav.
No, you continue.
Yeah. If you go back to that image with a man standing besides Optimus.
This one.
Yes. So in your analysis, or maybe in this new hand that we see 3 degrees of freedom for the wrist, or at least two maybe. But historically, I remember, because I've seen one of Tesla robots in one of Tesla showrooms, and the wrists are 2 hydraulic cylinders, or linear.
I'm getting to that. I've got a slide for that. Okay,
great.
Don't worry. But it's a very good question, because the comparison, especially when you look at the tennis ball Optimus here, I know it's a little bit small, but the right hand is the old one, and it has those big Popeye forearms, which are the linear drives, which create it's basically referred to as an SPU, a spherical prismatic universal joint. It's a parallel joint, and it's really fat. I mean, there's no doubt about it. And then you look over the other one and say, well, wait a minute, how's the wrist move? Don't worry, it's still a 3-DOF. Actually, technically, it's a 1+2 wrist. So there's 3 degrees of freedom, but the other one rolls underneath. You should really consider it a second elbow joint. Okay, so it's like 2 DOFs at the elbow, one which rolls the whole wrist, basically like our arm does, right? When you do that, you're all the bones underneath are kind of rotating. It doesn't happen up here, but up here is where they have 2 degrees of freedom to do the pitching and the yawing back and forth. And I'm going to get into the mechanism, how it's there, and we're able to see that. But I'm glad you bring it up. Put a pin in it.
So that's where the rotation is performed. It's all the way up in the elbow, so actually part of the elbow joint.
Exactly.
It's just the radius rotating around the ulna, or the other bone. So that's where you get your rotation, and then you have, of course, flexion and the radial and ulnar deviation. But we can also do some kind of circumduction there, which I guess you could do with this piston design as well.
Yeah. And circumduction is just a fancy word for like orbit around something rather chaotically. It's kind of the way it's just well, it's not really a pitch, it's not really a roll. It seems to be a combination of the two going around at the same time. Yeah. So
all right. So
now then I mean, there's a couple more images here. There's nothing really to say about this image, but this one gets interesting. Elon did point this thing out. It says, "Oh, you can see him testing the finger as it's being assembled," and going to zoom in here a little bit more so you can kind of see what's going on with that finger. So you can see there are 3 tendons that are coming out, and he's pulling on the flexure, which is the result of then getting the finger to close. And I'm coming in even closer here because I want everyone to see a little bit of the structure. And again, Gustav, this is rather curious, is that I believe I highlighted right here now. I circled in red where the ab and adduction happens. And that's going to be mounted onto the palm. And that is your point of rotation there. Now, just a little bit above that, where my cursor is right now, is where the first metacarpal, or where the not where your CMC joint is.
MCP,
or not CMC, MCP is right there. And that's like the first axis of flexion. That's you see offset in a bit high, and it's sort of like Gustav was saying, it's really buried down a little bit more. It's not at the crease of your skin; it's in a little bit further, but they have it up there. But the more interesting thing is I've sort of circled in purple here where they pot the tendons. So this is the point of attachment, that they've got these these strings that are coming in, and you've got to fasten those strings in there to be able to pull on it. And if you sort of notice that this then has to go through a little slot in here to come through, and then make its way through the palm and all the way through your wrist to get on down there. And the whole point of this is these are the ab and adductions. which means they're trying to make you rotate about this red thing. Why are they attached up here and not just right there? Because effectively you could do the same thing there. It goes actually past that joint and up into there. And I know why, and we'll get to that. Okay. So again, you can't leave the live stream because now I'm just going along and making sure that you stick around because you want to find out it's coming, building up the tension. Yes. Here we go. So again, this is how we can see how they are attached onto the palm itself. So these are the actual points here of rotation for abduction. And you can see back here is where that point of flexion is. And you can see both of these tendons coming up where they're potted and they're there to be able to give you a little bit of the abduction. And now you can also see up here the red strings here, or the red tendons that come here, which are your flexures. So I'm going to ask you, Gustav, if I pull just on this side here, which is the blue one, we're going to get what? That is abduction, correct?
Mm-hmm. Yeah, ab.
And then if I relax that, again, this is like horse's reins. You can only pull in one side at a time. And all you can do is relax this one. Nothing will happen if you relax it. You got to pull in the black one, and the black one will give you adduction. What would happen if I pulled on both of them at the same time?
I mean, ideally, you would get your MP flexion.
Yeah. But they've got that pink one or the red one in there for flexion anyway. So why? I mean, isn't that a bit redundant? Why would you end up doing that?
I mean, we want to be able to do that. It's a big handicap if you are not capable of independently flexing your MP joint. Now, there are some engineers on X who can independently flex their DIP and PIP joints. I never understood how to do that.
A lot of practice, yeah.
Yeah. So, but in our case, usually when you bend one joint, the other kind of follows along with the long. Even if we have two flexors, that's basically how we function in normal. We like to have this in order to grasp around objects more and not just have a curling motion of your fingers. You want to be able to close your hand around circular objects, and also certain things where you want to pinch with the whole finger or grasp around the guitar or whatever. So it's a really nice function. So in our anatomy, we at the same time perform the extension of the individual joints with the same muscles. So the long tendons up here, they don't really do this. They do this motion when you use the long extensor, the long stretcher, or the extender of your fingers. That would do this motion, and then you use the muscles in the palm to move the joints out here. So they won't be able to do that if they have the attachment here. They won't emulate the stretch of the IP joint, the IP and PIP. But at least they should be able to do this. And in some of the motions, you can kind of see doing that when it's like playing the air guitar. It's flexing the fingers without the full curl. Right.
And we'll cut, but you're right. One thing it does, it gives you a bit more control here, which something that the extensor could do with antagonism to help you do these weird things with it. But I think there's a third reason, or three reasons for doing that. And that is when you want to grasp something, you want to have a power grip, right? And the joint where you need to really get most of your torque is right down there, right? And that means in effect, I can get 3 actuators to help make sure I've got a good clench, at least at that first joint. The others are going to be a little bit weaker, but usually that's the one that's going to be supporting a load, right? When I come up around there, the payload that's going to be on the first IP, or I guess what is the proximal phalanx, I guess you'd say. It's not phalanges, it's phalanx, or single phalanx. That will then make sure it's a little bit stronger. So basically, you've got 3 actuators there that are helping out. And when you do the differential business, you can get a little bit. So that's kind of why they did the offset. And then unfortunately, why that motion is a little bit high. And that may come down to something else, is that you were kind of alluding to. This is something that really disappointed me, is that yesterday when we saw, I don't have the video up, but maybe you'll be able to show it. It cannot clasp correctly like that. So if you want to grab a pen or something like that, you want everything to close around. And you notice Optimus came down wrong because they didn't get the Fibonacci sequence right. The medial phalanx is too long. You just look at that. It just didn't close right. And maybe the pivot point is a little bit off or something like that. But I was really disappointed when it came around. It can't, there was a big hole going right on through there. I think
Which does
maybe
not
it shows
bode
up on one of my
well for
slides or not.
stability.
I'll have to see. But that was like one thing that kind of shocked me, that was not working correctly.
So that
The other thing is
doesn't bode
the
well for
fingers are all the
grid
same
stability,
length
does
as
it?
far as I can tell. They don't actually have a pinky. Yeah.
All right, let's carry on with this slide.
Yes. Now, here, I think we're ready for the next one here. This was kind of a revelation. Looking a little bit at what's going on is that you see he's just pulled on the flexure. And what happens when he releases that flexure? So when he releases, this is what's going to happen. So everyone take a quick look at this and tell me what just happened.
There's a spring there probably, as of all the other robots.
Yes.
It doesn't release slowly like our human finger would, right?
Yeah.
It literally springs into full extension.
Yes. Basically, I was expecting that there would be an extensor tendon because I identified something that looked like and I was absolutely wrong. They don't have that. They are using some kind of like basically a rubber band, not even a spring, to do that. And we can kind of tell because we can see it. And I think some of the images here, let me see, we go ahead here, is if you look right up in here, when it is the hands, okay, so here's kind of a picture of the hands closed. You see, they don't grip correctly there. But you see this little white piece here and another one there, one that's sticking out. You can go and you can see those. And those are basically the rubber band extensors, I can say. So they're more ligaments than they are actually tendons because they're designed. Now, I don't know if it's individually in each one of those IP joints for closing or whether they have like a long stretchy string that goes all the way back to the base that allows it to pop back. So we could see when he was doing the assembly, there was no way that finger was able to open up like that or extend itself because there was no tendon to do it and no other obvious means of being able to. And again, this is something that's common in a lot of other hands for being able to do something like that. And okay, I'm getting ahead of myself here. I want to find somewhere I had a list. Let me see. And I lost it where I show some examples here. Where that is, and I thought it was like next in my slides, and oh, there we go. That's the one I want to show right there, and we'll go from the current slide, and we can take a look at that. So this is in Mirdad. I think you're pretty familiar with this hand. This is the 1XDO hand, and I've sort of highlighted right here what I thought were also extensor tendons, and it turns out no. Those actually are not tendons, but they are the return mechanisms, and they are not rubber bands, but they appear to probably be black O-rings and you can sort of see the profile that's in here. So it's actually a circular ring that goes around there that comes through on both sides. And then it's embedded or potted right into the IP joint and to the phalange and then allows it to spring back open. So you don't actually have control of the speed that it opens up or the antagonism that you might want to have to be able to do these weird kind of movements with your fingers. So, that's just one of the things I wanted to point out there. All right. Now, again, if we go back to this open palm, you'll notice there's lots of colors here. And do you notice a theme going on? Well,
I'm colorblind. So.
Oh, really? Seriously? Because if you look up here on the fingers where the flexor tendon is, you'll see they're all red. And if you look a little bit closely down here where the abduction is happening, you'll see it's blue, black, blue, black, blue, black, blue, black. And there's also a similar kind of thing going on in the thumb. It's a little bit harder to see. We'll try to find an image for that. And right down here, that's not a blinking green LED, which was fooling me for the longest time. That is actually a piece of green yarn or string, or I'm suspecting it's Dynama. It could be Vectran, but it could be Dynama, which is the two kinds of materials that they typically want to use in these tendons. And the other thing we can see down here, these tendons are not sheathed. They're actually running directly through all these raceways because we can see how straight they are. They don't arc at all. So what that means is that if we look at the hands, we can kind of come up with a color coding that's going on there. And basically, this is the color coding for the hand, is that the flexures are all red. And then you get down here at your ab and adduction, and it's blue, black, blue, black, blue, black, blue, black, blue, black. And then you get the green, which does whatever the funky thing is, it's going down the CMC joint and also to make the fifth metacarpal or the pinky kind of come around on itself. So that's the actuation that's going on there. In some cases, the return for all the reds and for the greens are all being done with rubber bands of some sort. So you'll see there, everything comes in fives except for the green, which means the total sum of tendons here is 17. So that's pretty much where the mystery of what my little post was that's coming on out there. Again, I think we're seeing some flashing green lights that are going on here. Let's get on down to, we're going to get to the wrist in a second. Yes, that was where I wanted to get. And there we go. So again, if you look at these things, that's exactly what I'm doing, is I'm adding up all these different things where the B means abduction, red for flexion, and then the black for abduction. And that's basically what's going on. So that's my little equation to count up exactly how many we have. Okay, so we can also go a little bit further on down here. And part of what we want to do is, again, can't remember the order of my slides. Right now, we're trying to figure out how that wrist mechanism works for you, Meredith. And when you look at some of the videos, you may see these linkages moving around. So I've sort of highlighted right here for you what is one of the bars in the back, the linkages that help this mechanism to work. And on the left is the original Gen 2 mechanism that we see with the Popeye hands. This is my simulation of what that kind of looks like. And my guess is that this is kind of how the Gen 3, I guess what they're now calling the V3 hand, works. And that you'll see on the left side, that actuator needs to have a Heim joint down at the base in order for it to be able to articulate back and forth. It's just pure geometry. You've got a triangle there. You change the angle of one of them or the length of one of them, and all the angles have to change. So there's no choice. So that means if you don't want it to bind up, you have to move it around. Well, if you want that thing to stay inside of a tight area and not move around, this is the other solution, is basically you break that connecting rod into two pieces where it's able to now articulate and do that. So once you've seen that, and then you start looking at the movements, you sort of can't unsee it in some of the other places that are here. So we'll see right back and see, I get my ordering again, all different than what I remember. Okay, so there we go. So we can now see this green is the pitch joint. And then you've got this red here, which is the yawing back and forth. If you look really closely without my drawings on there, and it's because it's painted in black, it's very hard to see these two connecting rods, and right down there is the actuator. So the actuator is sitting in there, and there's it comes straight up. There is a pivot right there, and kind of like another pivot that goes through this handle that sort of allows this universal joint. And basically the green and the red are forming a type of universal joint to get that articulation. So that's how they're able to do it. And so Meredith, I hope that answers your question on how that was being done.
But I have concerns about it because this can overlock itself basically in some scenarios. Firstly, and secondly, I don't know how it would behave in back drivability situations. So somebody the hands externally, and how would that react?
Yeah, exactly.
Exactly.
It will be sort of difficult to transfer everything back. Part of the reason they came up with this architecture is they need a carpal tunnel to be able to get everything to go through there. And my concern is that that's really bounding closely. Like the original one, they tend to have these bundles that went through there. But this one, it just looks like, let's just take a zip tie and see how close we can go in there. These are not wires. Okay, you can't just zip tie them together. They're actually moving back and forth in there through that carpal tunnel. And there's a lot of friction between them. And we're also going to start to see the organization that they have everything is that they basically have actuators on the left side that are controlling fingers over on the right side and vice versa because of the way everything has to cross through there. And
but do you think these are they exposed? I mean, in this old falling apart deck sand, the tendon is like encased in
it's not encased. It's not encased. There's no sheathing.
There's no sheathing in this. So the color is the actual.
Yes. The problem they've been having is just this problem that everyone has with tendons, and that's reliability. And part of the reliability, everyone thinks, well, the tendons are going to break or they're going to creep, and it's difficulty of calibrating them. There's another problem, and the major problem is abrasion. And abrasion is what caused things to break. And sometimes the abrasion isn't actually causing the tendon to break; it's causing things it's rubbing up against to break. And one of those things are the sheaths, and the sheaths don't last. And like this thing about your bicycle, you've got that thing around there. It's just kind of able to handle that. But the constant back and forth here, it doesn't do it. And it's arcing around and they're getting their way. The other problem you have with this is crosstalk. Two types of crosstalk is that when one of those tendons is moving, it's rubbing up against the others, causing them to deflect a little bit. But then when your wrist goes, and Gustav, you're very good at demonstrating this thing to us, that basically our hands, the fingers that are on there, as you move your wrist, your fingers actually change position as a result, because the geometry of how the tendons pass through the carpal tunnel over to where they are causes the tension in them to change. So there's like crosstalk issues and everything else, reliability, which is pretty much why they're not moving ahead with this hand and why they could not get the reliability of it. And this is why it's gloves off, because they're not afraid of showing everyone anything, because they know that, to use a German term, this hand is Schrott. It's not, they probably only hope their competition is going to copy this at this point, because it has tons and tons of issues. And that's like part of what's going on there.
How far do you think they have to go to get to the final version of the hand that they'll unveil in April?
They've probably learned a lot, and they're trying to. It may be that they're going to be changing the actuator count. I've got a couple of ideas of things I might do a little bit differently. One of the problems that you see is, again, the abrasion. Is that Dynamat and Vectran are very good in abrasion, meaning they can rub up against things really well and not necessarily break. But if they're rubbing up against aluminum, they actually chew into the aluminum like crazy, so you don't want that. So you have to find a material, and it turns out that probably a material like nylon or something like that's a little bit better, because it's a little bit more slippery. It allows it to go through, and that's something else that they have to try to figure out and work on. And you'll just notice how they have to route everything through here.
Yeah,
so
pretty crazy.
Just take a look at that side. So that is trying to route 4 of them on one side, and there's one on the other. And this kind of helped me figure out what's actually in the ring. So if we look closely at the rings, we will see the very top ring consists of only 5 actuators. And they're the 2 greens, and then there's 2 blacks and 1 blue in the middle. So that's what's going on there. You go to the ring underneath it, and you'll see that they're kind of grouped. There's a group of 4 over here and a group of 4 over here. And this is basically the color coding on them. And you can see the others going. And so there's 12 down there. So 12 and plus 5, of course, gets us 17.
Planetary actuators, right?
No. They're micro ball screw drives. So if you remember a few weeks ago, something leaked out of China about what the bomb was and who all the suppliers were. And in their listed, something was like a ball screw drive. And at first I was like, ball screw drive? No, those linear actuators they have are not ball screw drives. But then it mentioned the hand. It's like, oh, that makes sense. So when you make them very small, they're probably going to be a ball screw drive as opposed to a planetary roller screw. So that kind of makes sense. That's what they're using. There's just tons of kind of interesting is like the connection right here. So if we zoom in on one of them, we will see that in order to pot or seat this in to the top of the actuator, they have to come up with some kind of connection strategy. And it looks like you put some kind of a cylinder, or you crimp something onto the end of that string to keep it in place, like we're all used to with our bicycles. We have something like that. And then there's a little clip that goes in and a collar that goes around the clip. I speculate that might be a type of circuit breaker that if something gets overloaded, it might be able to slip out of there or pop it off without causing failure anywhere else in the system. That's possible. And I think that, so I can go on and on, as you know, but I want to, remember that there are other people here that haven't had a chance to present very much.
We haven't heard from sorry, Gustav.
Yeah, just the last clip. There you can really see this tenodesis effect that we call it. So when it's flexing, the fingers can't really stay still. So when it's rocking the wrist back and forth, it will kind of stretch the fingers. You need a lot of control to compensate for that. That's why I think it comes here now when it does you see the index and the little finger kind of dancing around because of this tenodesis effect. So
exactly.
The ones who manage to put actuators inside the hand, they skip that problem. But then, of course, you will have a big hand if you're going to have 17 or whatever actuators in the palm.
Am I safe here to say that I don't see anything innovative in this hand.
Correct.
I agree.
I mean,
Okay.
I remember the DLR hands. I saw them in Automatica in 2015,
Yeah.
and they
Yes.
were as impressive as what you
Yep.
see here, and that was 10 years ago, right?
Yes.
Or even Rob
the
Knight,
shadow hand.
the greatest roboticist, he has a lot of tendon hands, open source, that are as complex as this one. So
I'm-
sorry, but I don't see anything innovative.
Yeah. Don't worry, and I'm glad you're here because I was afraid I was going to also make a lot of Tesla fans a bit angry by saying that
It's okay. I can be the only bad guy in this meeting.
I feel that I was underwhelmed by the hand,
Yeah, we said
again,
that
that's the
before. It's
reason
like
why
a-
they revealed this.
Yeah.
And the thing is, Tesla's also underwhelmed by the hand because they didn't mass produce this thing.
No.
That's part of the reason they said, "Whoa, we're putting a stop to this." Okay, so we want to stay grounded here and understand what's going on.
Yes.
You also notice that there was a post last night where Elon mentioned about the V. He said that's the V2 hand. Make it very clear you're just looking at water under the bridge here. The V3 hand is going to be awesome, like as usual. So we don't know what that is. He has said that the V3 bot is going to be different, basically from head to toe. There's not going to be anything left over from the original design. So everything is.
And he
is
also
going to
said
change.
that there will be iterations every year.
Yeah. Every
With the bot.
every year. So
Yeah.
they probably learned quite a bit from this. But yeah, there is nothing special about this hand. Absolutely
Yeah.
nothing.
Okay. So I want to get in a quick comment from Brian and Chris. We haven't heard from Chris. What are your takeaways, Chris? Let's go with you first because we haven't heard from you yet.
Well, I would defer to Scott on expertise in terms of robotic hands and all that stuff. It was great to see what he was presenting. I was also hoping to get an opportunity to discuss this larger in the context of robotic factories and scaling. And, the hand is a great part of the conversation, but, I think we'd had areas of energy and space and how this might scale in terms of robotic manufacturing that I would be quite interested in exploring.
Yeah, absolutely.
So that's what I want to discuss as well. I have that
Yeah.
ready to go, discussing the chips and the energy part of things. The one thing that Elon said was for the human robot was three things: hand, you get to get the great hand, and then you have to have a real world AI, and then you have to have manufacturing at scale. Those were the three things he talked about. And I think that there'll be some stepwise movement towards each of them, because good enough for 1 million useful robots in around 2020, late 2026, 2027 to get to that. And then 10 million, good enough for those 10 million use case. So you can have a 1 million robot use case. So in factory where you're adjusting things or some other stuff, and then the 10 million bots there in the year after, and then going to the 100 million bots probably takes 2 years to get to that. So they'll have the series of steps, and the question is, can they hit whatever design threshold they need for that first bit? And I also think that the chip aspect of it is something that can alleviate the need for perfection on the hand. That they can, the AI5 chip in volume will have the extra capacity for the distributed AI. So that will be where he mentioned the $100 to $200 per month to use the chip. That he'll say, okay, you bought the car with an AI5 starting in 2027. You have an AI5 with a bot having that, and I'm gonna pay you $100, $200 for that. So if I can get down to 20K, and I'm paying you $200 a month, then you might be okay with that. Many people may be okay with it if I have at least some other utility for the bot. So then that lowers the threshold of what it has to be. And also, if they wear out,
Brian, you think that's the
Go
bot? Because I thought he was talking about
The car.
the Tesla cars.
Yeah, well, probably both.
I think it's any form factor that you're buying the chip with the
Right.
product,
Of course.
then you can then have this thing work out. So there's some steps to this. So long as you can get, enough for your million bots, whatever your use case is, then if I close on that, I can say, go ahead and make my million bots. And then if I have to, if they're not durable enough, to Scott's point, right, that they wear out, it's just like hardware 3, right? In the cars, right? I may not be able to use it. Maybe I have to replace it. The fact that it may wear out in a few years is kind of like, it's an early product, right? And especially if I sell it to myself, then it'll be, not a big a deal. I just replace them. Okay, I got my better arms, better whatever, replace it. Especially if I can get it so that it's easy to replace. Say, from the forearm down, from the shoulder down, pop them out, and then try again, upgrade, that kind of stuff. So, but they may say screw upgradability because I just need to get these out, and then you will buy a new one. Just like you'll say, okay, screw upgradability in the hardware 3, you're going to get the hardware 4.
I have a question.
Yeah.
Do you think we're going to see the first? So clearly this year, they I think it's about 500 or 1,000 bots that they're planning to kind of build, mainly prototypes. That's going to be AI4, right? Hardware 4. But when they start scaling up, is that going to be hardware 5 or a mix of 4 and 5? What do you think?
It's a mix of 4 and 5. Because on the diagram where they showed it in the annual call, they had an actually misprint like A14. It's AI4 and AI5. Because if I'm starting to produce them by the end of next year, AI5 is not in volume until the year after, 2027, right? So you're going to have your first bot being AI4, and then you're switching to AI5. Yeah, so that's clear. Yeah.
If I can add a little to this, maybe the important thing to milestone is the performance of the AI5 chip. And when Elon talks about specific cases, it potentially being 40x faster, let's assume that for the sake of just for conversation, it's 8 to 10 times faster. Ultimately, the transition from 4 to 5 is a manufacturing and logistics supply issue, where you say, if I'm going to build a machine, I want to put the best brain in it that I can for the money at the time. So this means that they're probably going to want to move rapidly towards the AI5 chips, and that it'll just be a matter of, it's not a matter of that the hardware needs it. It's more a matter of having the most capacity that you can at a given point in time.
I'm going to throw a grenade in the room. I totally get that we're trying to build a humanoid robot, right? And try to build a humanoid hand. But if I was going to build a robot, why not build it so the wrist can go 360, right? And also the elbow can go 360 and maybe even extend, right? The hand in semiconductor material handling, there are plenty of actuators, right? Whether it's a whatever, right? 20 years ago, it used to be called the $1 million move, right? So you have a 300 millimeter 12-inch wafer full of Intel Pentium chips, and now it's probably like a NVIDIA GPU. It's probably 100, might be a 10 million, if not a $50 million move, right? Moving a 12-inch wafer. I don't think they're going to move towards what the industry had talked about 20 years ago of a 18-inch or 450 millimeter diameter wafer. But what else I thought interesting, what Elon talked about was the AI he's building is using integer for inference rather than everybody else is doing floating point, right? So that is a certain X number of scalability, right? So honestly, what I would build, right? 360 wrist, 360 elbow, or maybe no elbow, and be able to extend. And then you could easily have it maybe at the elbow joint or at the wrist joint, and you could just put on a different, call it an effector, right? You're scared of robots.
Marshall, I guess you haven't seen the E-Atlas or some of the Chinese bots. Yeah, I've seen them dance. Some of them are. I figure has intentionally limited the ROM to be like a human-like ROM just because they feel it's a better data collection, that it's hard to train it to do something that we can't do if we can't hyperextend. The other, sometimes it comes down to like your actuation strategy. So you're trying to make your wrist as thin and as light as possible. But if you put all the actuators in there, which would give you the large range of motion, it becomes really bulky. So if you're using this parallel actuation strategy that Tesla has, the math just comes out that your range of motion is limited. So I kind of agree with you that if you want to do that, sometimes depending on the actuation strategy, you may or may not be able to do it. And there are those who are clearly doing it, like we see Boston Dynamics and others. Right. And I agree. I mean, it could be useful. I know there's lots of times I'm doing the plumbing. I certainly wish my elbow
Right,
could go
yeah,
the other
you
way.
could do 360.
Yeah,
right. Or
yeah.
there are people who are double jointed. But
Yeah.
you know, if I was Elon, right, I would be thinking, yeah, I've got the, you know, you've already got all the components, right? So you could build your humanoid robot with the full humanoid mimic, right, motions and all that, and limitations. And then, but what's stopping you from building other robots that are not humanoid like, right?
Yeah, there's nothing. And there's just like the switching from embodiment, which it looks like Google DeepMind and others are kind of getting there, that they actually are able to train on one embodiment and it moves to the other.
Right.
So it'll be interesting to see if eventually we can literally train humans to do certain things and put it in a quadruped dog. I mean, I always thought it was interesting looking at the Peanuts comics and stuff like that, and Snoopy's out there and he's catching the ball with his mouth, right?
Right.
And the thing is that dogs know that, you know, we're catching the ball and we throw them the ball and they know catch it with mouth. They don't catch it with their paw like we are. So I'm kind of wondering whether these different kinds of morphologies that you would have would allow you to move from one embodiment to another. It may be easy like to scale up to some, you know, Hagrid's size sort of bot that's basically the same. But right now we don't know how to do it. And so everyone is just like, let's just stick with what we think is going to work. And once we solve that problem, we probably will be able to deploy, because eventually there's going to be weird form factors. There's going to be little spider robots going to be running around in the walls, like checking things and, you know, catching mice and getting rid of them and routing like minute fiber optic cable through the house and all these other things eventually, because obviously the humanoid form factor was not designed to work behind my walls.
Right.
Otherwise, when the guy comes in here, he wouldn't tear my walls down just so he can get to the wiring.
Right.
Marshall, if I can add a little bit to your question, it's clear that you've got an engineer's mind.
I'm an electrical engineer. I'm a super geek nerd.
Right. I understood. I could tell first time meeting and all. But I'd suggest that you're trying to solve the wrong problem. What's clearly been established is the reason they're humanoid form factors is we want to make machines that can learn to do everything that humans do.
Right.
Right. That's the whole point of the economic engine here. Hence why Elon's saying the hand has to at least work so that I don't have to pull out a robot and put a machine in to do task X, Y, or Z. Right. So functionally speaking, in order to get to the billion of these things and to radically change our economy, we have to basically say, how do we proactively create artificial human bodies?
Right.
And
I totally get that.
And one of my personal conversations that I've also had with Roden is, and I'd be curious, I know, Scott, you and I touched on this once before. I suggest we already start changing the language from robots to androids to really reinforce that we're trying to create something that is human in form, actions, and functionality.
But I mean, if you look at the video of the production line, right? So I literally slowed down the video because I wanted to figure out what robot they were using. So they're using the FANUC, which stands for Factory Automation Numerical Control, right? It's out of Japan, and really Japan probably owns 90% of the robotics, right? You got ABB, you got KUKA. Really, US doesn't really have much of a presence, right? There, you got the Yaskawas of the world, and SoftBank is talking about buying ABB's robot division for about $4.5 billion. So extrapolating out 10, 20, 50 years, right? I could absolutely see Elon Musk and Tesla building the robots, right? The robots to build your whether it's Cybertruck or Cybercab or whatever else, right? Maybe even SpaceX's Falcon 9s or Falcon 39s, right?
Right. You're aware that the humanoid robot is Gigafactory 3, or the final Gigafactory. It is, in fact, the robot that is the machine that builds the machines. Right?
right.
And so to the degree that any gigafactory, whether it builds vehicles, robots, houses, whatever, there's this symbiosis between human-shaped robots that do the human components, where he couldn't have done this all under the Model 3 line. He's coming back to that and saying, I want an autonomous manufacturing system that if I need to insert humans, I will.
Right.
But otherwise, it's basically just going to crank things out and get all the benefits of Wright's law. And, you know, circling this back to specifically Tesla, There are the two areas that I'm mostly interested in exploring here with autonomous manufacturing. The first is with the unboxed line that he's able to potentially talk about reducing times to 10 seconds or less, getting 5 million vehicles on a line. And then the second thing was the clues that he had given us that Brian had mentioned earlier, that he's looking at a 1 million run rate by the end of, I think, 26 and a 10 million run rate on the robots by the end of 27. So if we just stop at 27 and go, you know, they've already allocated capital to the idea of building a factory that's going to crank out 10 million robots within the next 2 years. So that helps to set this leveling conversation. And just to add to what Brian was saying before, I've speculated that we move out to a 5x in the following year, and that ultimately, you know, I think I've got by 2029, we should be able to do 100 million robots. So then from that comes the secondary conversation, which is we're AI chip constrained, we're battery constrained, we're actuator constrained. And as Elon had also said, for both the vehicles and for the robots, this is going to require, let's say, a 10xing or more of the supply chain. And that's the weakest link, in my opinion.
Yeah.
I also want to just throw something here and say, I'm not really convinced if automotive manufacturers are the best to build humanoid robots. And I have good reasons for that. But the main thing is, historically, a lot of automotive companies have approached building humanoid robots and they failed. And the reason was intentions. So the intention was keep the investors happy and trying to do some PR and marketing. So that is my concern, to be honest, about the status of.
Oh, I'll go a step further with you, Mayor Dad. Do you remember the Volkswagen robot? Do you remember the Volkswagen robot? Do you remember the Acma robot, which came out of, I think it was like Rougeau? Do you know where Kamau spun out of? Remember GMF and the GM robot and stuff like that? So they back in the 80s, they all tried building their own industrial robots and they couldn't. And in the end, they either get spun out or they get bought up. So like Acma is now part of ABB. Volkswagen, you know, effectively that disappeared, and then KUKA took over that business. Fiat had to spin pretty much Kamau out to come up with its own separate division because, and the same thing with CAD. Remember where CAD started? It started in all the aerospace companies.
Exactly.
And then eventually, because they couldn't get it from anywhere else, so they had no choice to build those things. So I kind of agree is that they're going to be very myopic and come up with humanoids that only serve their purposes. And to be general purpose, you need to be a company that is not in one particular avenue. Tesla might be the exception. But
Tesla's not a
I heard something
anymore.
the other day in reading, it might have been like the Register or Business Insider, that GM is starting up like a robotics division for humanoids. I'm just like, oh, they're just trying to pump the stock because I know GM too well. Sorry, they don't have the chops to do it.
They did that also 12 years ago.
Yes.
I think it was Robonauts, right? The astronaut.
Yeah. They also tried to do a robot offline programming.
Yeah.
Back in the day when my company came in there, we basically had to show them how to do it because they didn't know how to. So, yeah, a lot of these companies, they have the need, but they don't actually know how to solve the problem.
And I would add to that regardless of who the robot maker was, whether Otto or whatever, the reason why they all failed is we didn't have AI. We didn't have neural nets. That's the key ingredient that leads us to the iRobot future. And the ability to do the learning and scaling is to get rid of all the heuristics. So, you know, those were our first attempts using incredibly crude tech. And, you know, robots cannot proceed without neural net brains.
Okay, so I think if we've had enough of bots, we can carry on because there's a lot more to chat about. And Brian, you've got a few slides for us. Let me just cue them up and you can take us through them. There we go.
Okay, so what Elon said on Twitter, X, as well as at the annual meeting yesterday, add those things up. He talked about making a fab that would make 1 million wafers per month, and if you have about 100 chips per month per wafer, that would end up being about 1 billion chips per year, and that needs to be a terawatt per year. So we already have a problem where TSMC in their April tech symposium said that they would go from 7 million chips per year to 50 million chips. And then you have the Samsung factory in Texas that's going to have about 300 wafers, 30 million chips, going to 2 million wafers and toward 200 million chips. So a lot of chips that we do not have the power, even as fast as we build new natural gas facilities, making a lot of solar and batteries to try and offset things, because you have to, increase the power, reduce the power load in certain areas so you can get more of your grid load onto these things. So 2030 definitely need 100 gigawatts per year, maybe 200 gigawatts per year to light up all the chips that you're going to make. And then if you're going to make even more chips, again, you have this huge problem of powering it. So that's where the space-based solar power comes in. So I can go to some next slide. So you have the AI5, and this Starship is the key to all these things. So finishing the AI5 chip, AI6, AI7, AI8. So we're going to many series of chips, AI5 in volume 2027, AI6 2028, AI7 2029, AI8 2030. So you're going to step through a series of these chips that's going to be high volume. And then they're going to work with Samsung and TSMC in 4 different locations to try and get all these chips, which is fine to solve that problem. But then you end up with the problem of how do you power them, right? So it's going to be everything natural gas, solar, and everything like that. And then the performance scaling of each one. Go to the next slide of that. So in a regular data center, $35 to $50 billion or so for each gigawatt of these data centers. 70% of those is chips, and then 20% power, cooling, and other infrastructure. So the question for the $10-15 billion is, can we put a gigawatt up in space at roughly that cost? And then there's some wiggle room there, because if I cannot power them any other way, then I may have to pay double or triple, which they sometimes do for the natural gas, or I'm waiting for it. I just need to have it because the economic forcing function is such that I need to do it. Reducing the price of the chips, part of that is Elon making them himself with AI5, AI8, where he doesn't pay the 70% margin to NVIDIA. If you buy the NVIDIA chips, he has to pay that amount. But if you can get roughly equivalent, and he's talking about 1/3 the power usage for AI5 versus a B200, and then getting to 10 times the inference, and to reducing the cost and those kind of things, which by then, 2027, NVIDIA will be offering the Rubin chip, which will have 5 times better. So he wants to get roughly in the zone where cost-wise, production-wise, it makes sense for him to switch over to AI5 versus a Rubin. Okay, and then we can come back to this if we need to refer back to it, because there is insights into other aspects of this big picture, which Chris is talking about in terms of singularity. Okay, next. Okay, so then yesterday he gave 5 times a quantization for that, 9 times memory, because you need to solve memory and chips, because part of AMD's problem, part of other competitors to NVIDIA's problem, is that NVIDIA has contractually locked up a lot of the high bandwidth memory supply. So then around each chip, NVIDIA chips or other chips, anything doing AI, you'll have to have a lot of memory. And those are also limited. So Elon mentioned chip production as well as memory, high bandwidth memory, as well as packaging. So there's a series of steps that have to be solved for that. And this is looking at 50 times the compute of AI4. The main thing about the compute is must be competitive enough within a factor of 2 or 3 of whatever the NVIDIA chips are to justify switching over to the other alternative. Although the power limitation problems may force you down a non-optimal path, but you generally want to not have too many trade-offs. Go to the next slide. In terms of space, Jared Isaacman's now going to head NASA. So he's Elon's buddy. The main takeaway from that is that decisions around space working with the United States government Trump and Elon are again aligned enough so that Jarek Eichmann is leading NASA. So certain decisions that relate to the administration will, in general, assume to go Elon and Tesla and SpaceX's way. Next slide. Yeah, 5 again. Go ahead, next one. So I've compared some of the details around the AF5 to A8 chip. We can skip over that for now. Okay, so this is StarCloud. So they put up the one chip last week, and they have an analysis of 40 megawatts. Which,
right?
what?
It was the H100.
Yeah, they put up an H100. Right, they put an H100. By the way, the importance of that test is that we have never put up really high density chips without waiting many years to get them hardened for space, and so there's complexity there. Yeah. This is non-trivial to bring up chips from Earth to space. There'll be new testings around that. In general, you need to have more redundancy, more radiation hardening. There's a bunch of work that has to happen there to make it work, but they are moving toward doing that. Next year, they'll have their StarCloud 2 with about 100 chips, presumably more advanced,
Brian,
maybe B200.
If you don't mind, I just want to pause just briefly at that point and
sure.
Open it up to Chris and Scott, because we talk about off-the-shelf components in the new space economy and how this has radically transformed systems engineering, not only at NASA, but also at all the space startups in America and Europe and across the world. For a regular H100 to be up in space and crunching a bit of data, how mind-bending is that? Because we've seen in the past with NASA, the European Space Center, JAXA, ISRO, etc., to put up any sort of computability in space on the ISS or otherwise, you had to go through a long process of hardening it and getting it ready for space. What does this represent to you that you in this off-the-shelf revolution, Scott, Chris?
Well, there's a couple things. Part of it is that a lot of those components are going up there is space hardened, is because they're critical components. You just can't have them fail. And so if we don't have enough data on them, we don't want to put them up there, and there's a certain amount of risk aversion and everything else they have to go through. But I think the other reason is that you're putting so much money in one of these missions. The last thing you want is it to fail because some simple little chip that you decided to spend 50 cents on failed when maybe you should have spent one that was a little bit more than that. But at this point, things are throwaway. So a lot of the SpaceX satellites do not use a lot of what are quote unquote space hardened components. They're using a lot of off the shelf stuff on there because they're considered disposable anyway. So why are we going to spend $10 million on a satellite that we can put up there for 250 because our launch costs are so cheap? So I think part of the game changer is that we can flood the zone right now with so many satellites. And who cares? There's been a couple of missions where SpaceX lost them. Remember, they launched a mission during a solar storm and they should have known better. And they lost a batch and it was just like, oh well, they didn't care. But for any other company, it would have wiped them out. That would have been it. It's like, we spent 20 years coming up with that payload and now it's in the Pacific Ocean somewhere. So no, that I think is what tells us is that launch costs are going down so much that people don't care if the satellite happens to fail. And the thing is, this technology is going to be deprecated within 3 to 5 years anyway. So I don't care if that satellite is going to last 15 years. Because there's going to be a better one in 3 years. It's going to have 10 times the performance.
Do you think there's going to be some surprises in our learnings from this H100 in space? Because
it might turn out
Ingenuity, the helicopter on Mars, that was built with off-the-shelf components, and look how brilliantly it performed.
It may be that it defies all expectations and lasts a heck of a lot longer. Or the error correction and everything else in there is like way better than everyone anticipated. So the thing is, we're kind of in this the situation that to get the data, you got to put it up there, but no one will let you put it up there because you don't have the data, right? So it's this catch-22 that's kind of going on. So let's just put them up there, get the data. Maybe we'll be surprised. I mean, that's what ended up happening. They started bringing iPads onto the International Space Station, and guess what? Yeah. They work. And they work reliably.
In fact, if I can add on to that, I read the Project Suncatcher, Google's proposal, And they specifically discussed radiation hardening, and that they had found that the the TPUs were already particularly resilient. And as Scott had also been mentioning, one of the easiest techniques with these things is to look at them with some sort of error correction and say, you know, if an individual chip is going to get hit by a stray cosmic ray or whatever, that's what error correction's for. Just put many more TPUs out in space or AI chips, and provide an error correction, you know, cross-checking validation sort of mechanism for them.
And
Makes
guess
much
what?
more sense.
Chips down here on planet Earth get hit with cosmic rays all the time too. So
Yeah.
there have been a lot of documented cases where they tried to figure out why there was like some computational error, and they checked everything, and in the end they said it was a stray cosmic ray. So what that just means is that if you start building in error correction, you don't have to worry about it, because half the chips coming out of your, well, I would say a lot of the chips coming out of your fab actually already come out of the fab with a lot of defects in them, you know, and there's already these things to correct for them. And they know that over time, parts of these of your DRAMs and stuff like that are just going to start to fail, and so they do something. So it doesn't surprise me it's actually working in space, because they're already designed to be robust.
Yeah, and if I can maybe move on from, there's a note that I put here for you guys when we were talking about this orbital. What I have is a title called "From Terawatt Hours to Orbital Intelligence," and it basically sets up a core thesis, which Elon was echoing as well, which is that AI compute demand will outstrip all terrestrial energy sources and land constraints. The sun is the only scalable continuous energy source. Orbital intelligence is the end game. So in that context, everything that was discussed with Project Suncatcher or with this AI-8 chip or whatever SpaceX and Tesla do together is basically to move humanity to the Kardashev 2 model. One of the things that I'd taken out of the Suncatcher premise was AI is a general purpose technology like electricity, and that the demand for flops in energy is going to grow exponentially, and that one of the key things that I really liked was they discussed this idea of a dawn-dusk synchronous sun orbit that spends 97% of its time facing the sun. So if you basically think that there's a polar ring around the planet, this is the orbital path that we would install all energy collecting devices. I think that's a really good point in this, and you know, something that we should address, that whether it's just AI, whether it's energy collection or for an AI data center in space, this is a unique orbit that ultimately will be, I suggest, a staging grounds for orbital infrastructure. And the first steps are energy modules. And our proposal is to literally use the Starship's payload bay as, you know, an independent solar energy harvester. And then you could arguably say, well, inside of that, like what we're saying is every Starship built should have fold out solar arrays that are similar to what they're doing in Starlink already. And that each of these modules would also include Starlink with optical connections, yada, yada, yada. And we figured that we could probably get about 100 kilowatts in, you know, that kind of design that they're using for the Starlink already. And then out of that, you might potentially be able to power 100 AI5 chips. So in that case, the chips become the payload. But what we're looking at is, how could we make it that every Starship has this infrastructure of having solar, and then use the scalability of Wright's law to produce that as a component for every Starship that we build, so that we get the costs low, just like they're doing with Starlink. Thoughts on that?
How many would you have to put up? I mean, compare. I know nothing about this, but compared to like a giant data center that they're building all over the place now, how many of these would you have to send up to be like equivalent in?
Well, there's two conversations here. The first is when we looked at I think it's Star Cloud, they're talking about, we want to do a 4 kilometer by 4 kilometer array. So other than the efficiency of the solar panels, which already the Starlinks are like 33%, they're good tech, let's work with those. Basically, this becomes an area conversation. So if you say I've got the sides of a Starship payload bay, and I can literally horizontally have come out of the wings, not in the way that you've seen some illustration where it's a fan out, but instead that it's literally on the sides of the ship and it expands outwards for some distance. That's a mechanism that allows you to create massive amounts of area to do your solar. That's the first and foremost thing that you're going to need from any energy system. So what I'm saying is that we want to have, let's say it's every module that is a payload bay is also an independent spacecraft, RCS thrusters, all that kind of stuff. So just like a Starlink satellite has its orbital array, we'd say the ship itself and the payload bay section could be a free floating energy hub, whatever the case might be. So, if we were to just do the Starship, you can get maybe, I think, somewhere around 4,000 square meters with the proper tech. So the point that I was making earlier is, let's assume from engineering, we're just going to use 100 kilowatt hours per Starship. So you install the arrays, that's what you've got. You now have power for any Starship, whether it's going to Mars, whether it's doing AI, whatever it is. So I think this is an absolutely essential system that they haven't shared with us yet. Those fan out little solar arrays don't do it for me.
So I would say
Ryan,
that my analysis is that they will not go to the mega structures. It's just like they wouldn't say, let's stack up, 1,000 megapacks into a 100-story, thing of megapacks, even if there was some reason to do that, because there's no reason to change the architecture of their V2 minis to V3s. And Elon even had a post saying that they would modify a V3, a Starlink satellite, in order to do this AI data center, which, to your initial point of 100 kilowatts or 200 kilowatts and 100 chips in that range, would be what they would mass produce. That would be my thing, because the timing of this is that everyone runs out of power or gets really power constrained for the chips you want to build by around 2029, 2030. That we have to do huge lifts in order to keep getting power for these AI data centers, which can be done. So you'll make huge adjustments around 2030 to power 100 gigawatts, 200 gigawatts of chips. But if I'm going to even beyond what the Samsung factory can do, Samsung is going to go to 300,000 wafers by maybe end of this year or into next year, probably end of next year. And then that'd be 30 million chips, all dedicated to Elon's, that probably going to 2027, because they have a mass production in 27. So that 30 million chips is 30 gigawatts, right? So it's like a lot of power that they have to do. Even laying that up is very, very difficult. So because we don't have enough natural gas, not just natural gas turbines and stuff like that, which already are 7-year delays, it's also putting in new pipelines, new mines, getting in to the ground and taking out that natural gas is very, very difficult to do the scaling. And then the nuclear is not ready. It's going to take longer. 8 new reactors, a drop in the bucket, right? That's like 8 gigawatts, maybe 2035. If some other new company comes up, it's again too little, which is why we have 2.8 terawatts of solar nameplate. Nameplate capacity of solar is 2.8 terawatts now on Earth, 80% made in China. But the if I put them in that orbit that Chris talked about, now that solar gets 8 times better, right? All the existing solar panels, you can't just shove them into Starships and lift them up there. You need to make the new factories. But the principal technology, it would work. So then you basically go from SpaceX scaling. They have 200 megawatts up there roughly now, maybe 200 to 500 megawatts, based on 20 kilowatts per V2 Mini. They already have FAA or FCC or whatever approvals for about 30,000 or 24,000 V3s. They put an application for 15,000 V3s that are direct to a cell phone. So they have about 40,000 of those. If they're in the 50 kilowatt to 100 kilowatt range, you're in the 1 to 2 gigawatt range. Those are only silicon, some modified space-based version silicon, maybe not even modified that much, because they're willing to accept 10 to 20% degradation versus a gallium arsenide one that does 5 to 10% degradation per year. They don't care. Like, as Chris' point, they don't care, right? It's all about volume, cheap, enough, and then move it up. So next year they get the Starship fully reusable. They'll launch maybe, hopefully 50 times, something like that. There's issues the next year or two about doing enough for the Artemis lunar mission, which involved about 30 or 40 launches. They need to make more launch towers. And then in order to get this to be serious, in terms of the chips won't be the problem. It will be getting enough of the solar up there and getting enough launch towers and launches in order to make the difference. Because as we already have with the Samsung deal, the TSMC deal, plenty of chips. He'll have tens of millions of chips for that. And then can he light them up on the ground? If he can't, then the lighting up in space becomes the option, putting all this solar up there. And they already have done 3 gigawatts from their V3s, 3 to 5 gigawatts from their V3s, regular ones, and then they can put up the AI versions of it. So taking the time to figure out some megastructure, other stuff like that, they just don't have the time to do it. So then they just need to put up, many, many factories of solar for space in order to do the launches. So the urgency of the race is that there is no power to do it. And that's why you can even sacrifice cost. And if they go, it could take more cost to do it because I can't get below the $80 million for 40 megawatt threshold to compare to certain efficient ground things. It's like, I don't care because I cannot light these chips up any other way. And the chips have value for AI, where I make $100 billion a year for a gigawatt because of some doing it for coding. Like if there's a need for that, and supposedly there is because people are spending $1 trillion allocated by OpenAI to do this, right? They've already made commitments to $1.4 trillion worth of chips and energy and data center and stuff like that. That going beyond that, again, running out on Earth to light it up in the right way, and then also there's the cooling and other stuff. There's other reasons where you get limitations on Earth. Is that the big picture thinking is I can already make 2 terawatts, 3 terawatts of regular solar on Earth. I need to make versions that are light enough for me to launch, similar versions that go up to space. I have the transportation means to go because I can take up 20 to 40 megawatts per load. And if I do 5,000 launches or 1,000 launches, that would be 40 gigawatts, right? So a mere 1,000 launches and I'm off and out. I'll need to do roughly that number to launch my, I need to do 500 launches to do the 30,000 V3s, right? So you need to get to that scale. So the transportation systems can scale with thousands of launches. And then I need to solar, we can make it. I just need to make new factories to do it. And then the chips is already there. And that chip demand is where he's saying, I'm going to go keep the scaling law going. Everyone's going to go 1 gigawatt starting 2026 with 5 locations, Microsoft, XAI's, Colossus 2, et cetera. A bunch of guys with plans of 5 gigawatt facilities in 2030, and then other smaller ones going around. The next step up's 20 gigawatts, 100 gigawatts. If the other guys can't follow, and again, they'll pay for space. If the power solution is only in space at the 100 gigawatt level, then you have to keep stepping up and you'll distribute it. The other aspect of the distribution is if I make 100 million bots, that is distributed 100 gigawatts of power, of compute power. So the distributed thing is also a solution to the power using chips. I can shove 100 million chips into bots, or maybe 1 billion chips into bots, and those billion chips would be my distributed terawatt. So it's
Brian,
pursuing the
can I paraphrase what you're saying? Because I kind of want to get back to
yeah,
the core issues. The first
sure.
issue that we all agree on, including Elon, is limiting factor is energy in space. So the first project that we should scope out is how do I put a terawatt in orbit so that I need to power 1 billion chips? Like that,
Right.
that's the transition, right?
Yeah.
So, that's I think the key linchpin in doing planetary hyperscale intelligence is to have it all be in orbit. And the first step is how do we get to use, and this is where I'm going, Wright's law and scaling. And that's why I'm saying you go to Starlink and you say, listen, those panels you're using, I've got an idea on how I can load them up inside a Starship, use exactly the same stuff that you're doing now, and get lots more collection per payload. That's sort of the point that you're making, right? Now, then you apply them in, call it a Dyson swarm for the sake of conversation, but it's around the Earth in this polar orbit, so that you now have this planetary asset that just, the more you put up these same devices, small devices, you don't need a mega structure, you merely need to get them launched, as you were saying originally. Everyone, the Starship that goes up, it puts up another batch of them, just like it does with Starlink. And the reason why I'm framing it this way is it seems, if you've looked at how rapidly Starlink cranks these things out already and how automated their factory is, it's sort of an unsung hero compared to the Gigafactory. And I think that there's a real opportunity to make that the solar array component be a product in and of itself that just goes as part of the Starship. Does that make sense?
Yeah, so I'm saying that you have the satellite power and bus, basically the V3, that is the product. You can swap out the components within that. But basically, 50,000 V3s is the current plan for the Starlink next steps, right? That they start launching in 2026 with these 50,000 V3s, right? So then the 100 gigawatts is 1 million AI version V3 satellites. So you'll basically go 20x up, just like we've gone from.
But you're not going to be able. You're not going to be able to, unless, let's say, the V4 VX Starlink is 2,000 square meters instead of what it is now. You're not going to be able to power more than 100 chips. Let's say, I think it's like 10 kilowatts now. If you scale it up by 10x to 1000, you're going to have to build the data centers to be somewhat limited in terms of chips to handle how big the arrays can be.
It's right. So basically, with the standard rollout double solar, I'm saying you can get those to 100 kilowatts, right? You get that 100 kilowatt size. I think that the ones that they have for the planned V3s are about 50 kilowatts. So you just double that to 100. But if that becomes a problem, it's better to have chunks of 50 chips at a time versus stressing over making 100 or 200 chips in each one. And so they will be in that form factor, and then they'll have laser communication. They have some kind of formation flying if you want to get them closer together, right? But they will be in the mass-produced V3 format for that and they won't be as tightly clustered as you might ideally prefer, but you have to go to a distributed architecture in order to build this fast enough. At some point, maybe you can figure, can I cluster them together? The other thing.
Let me pause you on that though, because this is one of the cool things about the Suncatcher. As you may have seen, they're saying, no, we're going to do a small number, I think 81 satellites that have what they call a free space optical link, which others call a space laser, right?
Yeah.
And so when we looked at the analysis of this, it turns out that Starlink's laser is a 1.6 terabyte per second link. And if you basically say every AI5 chip has its own dedicated optical, and that those things can point to any other cluster, you basically could create a free space version of NVLink on an optical basis.
Mhm.
And then to your point, it's you're not going to have them go anywhere, but you could theoretically have data centers anywhere in orbit directly beaming data at that rate to each
Mhm.
other, right? And so ultimately, this is going to be mesh from an AI processing and information perspective, similar to how it is with Starlink, is that, the information can flow through the optical links.
Yeah. So if I could just throw in something here into the mix, and Scott, you'll remember this. Let me just bring it onto screen. So this is Ex Lumina. Scott, if you remember, we spoke to Kian Conrad Tajbaksh, the founder and CEO of Ex Lumina, who's building this kind of a prototype for orbital laser power grid. Do you see something like this? And I wish Kian was with us on the stream. I did try to reach out to him, but do you see this as contributing to the basket of energy that's powering these data centers in space, Scott?
I'm not sure that Kian pitched it that way. It was more or less to help a lot of the other smaller satellites that are out there. So you don't have to bring your own arrays along with you. You could put it somewhere else. And the idea is that you would have a very small solar cell on your satellite that you're beaming the laser to, because the laser is tuned to be at the optimal frequency. So you don't have to have a big array with very little losses. And the other advantage is that means your satellites not only can be lighter, they don't have to worry about the vibrations and everything else that kind of comes along with the whole idea of having these solar panels. So that means I think it was like the jitter they were talking about, that it could help a lot of that. So I'd certainly see it as helping quite a bit, but I'm not sure that if you're talking about a full-blown data center, which requires like a 4-kilometer array, it might be that it's almost better off having its own, being in that correct location. But there is definitely a spot for this. I mean, this is a brilliant idea from someone who is like already, I think they're getting ready to launch like a test satellite. They're very close to that. And he's only 20, and we were kind of kidding that he's going to have it already up there and his dreams realized by the time he turns 25. So it's kind of remarkable what this current generation, the Gen Zs, are actually able to do when they put their mind to it.
I'm curious to know what Marshall thinks about it, because he's the data center hyperscaler and the energy systems guy. What's your take on all of this, Marshall? You've been listening into it.
Yeah. Well, I'm gonna comment Brian's background on his Star Cloud -1, right? Already in space. Google's talking about it in 2 years from now, and listening to Elon's during the shareholder meeting, and also extrapolating out to Isaac Asimov's science fiction story. Now it's on HBO or Apple Foundation, right? Literally, I don't know, this could be 50, 100, maybe several hundred years out to the future. Literally, Mother Earth, the entire planet, could be blanketed with bifacial solar panels powering down to Earth, and also having all these data centers out in orbit. And then you have your AI assistant, if you will, right? That is watching you and telling you, hey, don't be committing crime. So this brings me to Tom Cruise's Minority Report movie of precog and pre-crime, right? So let me point out that the whatever industrial complex of incarceration maybe would possibly disappear, right? And
that's not good for people like you and me.
Right. But I mean, I look at this, right? I don't try to look at all the details of solving those issues, because, I'm sure that when Elon Musk sat in that conference room and said, we're going to build rockets that's going to land itself, and I'm sure everybody else in that room was rolling their eyes, right? Thinking, what is he smoking? And where are we today, right? And not to mention, Star Cloud's already got an HP 100 in orbit and collecting data. So I think it's just a question of time. It's not a question of if, right?
So, Scott, you had something. There's an interesting post that you shared with me, and I just want to bring it up so you can take us through what you had in mind before we get back to Brian's
it's actually, there's like the second post. This turns out to have been a reply to the actual overall post, and that is SETI Park, as you may know, on X, digs up all sorts of very interesting patents, a lot of Tesla patents to get an idea of what's going on with Robotaxi and the production process, as well as other different robot companies. And he found one for SpaceX, which when you kind of read through the patent, it goes, oh, they're already thinking of doing exactly this, compute in space. Now, they didn't say like data centers or servers, but pretty darn close to it. And part of the key is the communication between the satellites. So right now, 25% of the Earth is land. The rest of it is ocean. And of that, a small percentage of it is populated. So that means, probably 15% of the time, these satellites actually are needed to do what they're designed to do. And that is act as an internet service provider and communicate between the Earth and somewhere else. And 85% of the time, it's sitting around waiting to actually go over a ground station or something like that. So since it's up there and it's already collecting energy and doing all this other stuff, and it's got big onboard compute, why not use it for that the rest of the 85% of the time? And since you have these laser links, you can compute, you can take whatever that data is and offload it pretty quickly. And they talk about in that of, potentially using it for like crypto mining and inference and a bunch of other things. So it's just like, the main thing is SpaceX has already been thinking about this for a long time. So we shouldn't be surprised that they're on board. And when I'm talking about, it was it from Google or Meta, the group that has come up with this this first idea, this data center. When that went out, again, there were a lot of people who thought it was a crazy idea, and a lot who thought it was great. And a big discussion on X of all the naysayers saying like the 1,000 reasons why it's not going to work. Yet it's interesting. There's more than enough to say it's not crazy, because I guess Eric Schmidt kind of kicked it off, didn't he? He was the first one. Everyone's been looking at it, and the more they're looking at it, more and more are getting on board. So I'm thinking the people who are saying it's not going to work.
Comment that really got it going.
Yes, probably the people who are saying it's not going to work maybe haven't revisited the problem and really looked at it and examined the rationales and their arguments and why it's not going to work, if there's that many people who are convinced that it will.
And just to add to that, one of the interesting things about these constellations of data centers and the optical links, like we said before, an optical NV link, is they're all coherent. So you could make a mega system, with as many as you want, but secondarily, it allows you with the ability to point to each individual cluster to create dynamic training systems in real time. So you basically just assemble, these people are part of this same or these satellites are part of the same transaction or cluster, and the optical links keep everything in sync because they're so fast.
Right, and don't forget, right, if you look at it, I think Elysium, Matt Damon movie Elysium, right, they had to send the poor kid up into space to be treated by the automatic machine, right? So that is probably in a reality soon. I don't know how far out that is. And you look at what I am sure Elon has got a grand master plan that he's not necessarily disclosing to anybody, but maybe to a very few inner circle. With quantum computing, right, in space, you could, with lasers, so you could be beaming power and data. And the people are already working on cooling direct to chip, right? So you've got immersion cooling, you've got liquid cold plate. Liquid cold plate seems to be the most prevalent right now, and I think direct liquid to chip is going to be the next phase, right? So whoever gets those stuff figured out is gonna have a large say and be the first to market, right?
No, I'm glad you brought that point up, Marshall, because one of the most and I have to also ensure that we talk to a wider audience that's not always as technically clued in as our star panel today. Cooling in space has been one of the big points of debate that have been debated in the wider audience, and it's important to know that conduction and convection that works on Earth will not work in space. So radiative cooling is the way to go. And Brian, you and I have talked about it recently. Scott, we've talked about it. how would you explain the problem of emissivity, and how do you solve that? And this goes out to all of you, Marshall, Brian, Chris, Scott.
No clue.
Yeah,
But
well,
some 20-year-old is going to come up with a very innovative solution. Right?
Yeah, the main thing is, in the end, all heat transfer is radiative. It's nice to have conductive, and it's nice to have convection. But in the end, the energy that gets transferred from one to another in a lot of cases is actually done radiatively. So the best way to actually transfer heat, in many ways, is the radiation. And turn your stove on and get it really, really hot. Now, when you touch your stove, that's conductive heat transfer right there. All right. And that's really pretty bad. Putting your hand above the stove, you might be feeling some convection as the air is going around there, but you can stand a distance away from it and still feel the heat. And it's not coming from conduction, and it's not coming from convection. It's actually coming from radiation. Radiation that's one way of heating. Radiation cooling can also be pretty useful. Right now, it's November here in Michigan, and in a few days, I'm pretty sure we're going to have a clear night, and I'm going to go out to the neighborhood pond. I'm going to look at it, and the ambient temperature will be probably 39 degrees, yet there's going to be a thin layer of ice on that. And explain to me, how is that possible to get a thin layer of ice when the ambient air temperature at that time was 39 degrees? It was not doing that through convection or conduction. It was doing it because if we have a clear night here, we are looking at a heat sink that is 3 degrees Kelvin. And it's that heat differential that actually causes a lot of it. So space is in some ways almost the best place to dump your heat. The problem with being in orbit is that you might only have like half of your hemisphere pointed out into the inky blackness of space. And the other half, you might be pointed actually back towards the sun or back towards the earth, where you get a lot of that back. So you don't necessarily get that for free. So some of those things have to be taken care of.
And every time you cross the terminator line, you've got problems.
Right. But it goes to the fourth power of temperature. Okay, on the Kelvin scale, not Fahrenheit, not Celsius, but the fourth power. Which means if you just pump up the heat a little bit more, you can dump way more than you can through any other methods. Now, not to say that there still aren't going to be issues. And again, a lot of times the problem is you better make sure when you're dumping that heat out, there isn't some other satellite that's coming around and suddenly you're dumping it right towards it, because that kind of radiative heat transfer within satellites themselves are a problem. And they have to be very cognizant that they don't have some other surface on the satellite, which is very shiny, that will actually bounce it right back at the element you're trying to get rid of it. So there's the reason why things are colored the way they are, to try to prevent things like that.
But
so
just give us a sense of the enormity of the problem. The ISS has what? Correct me if I'm wrong, but about 70 kilowatt equivalent of radiative cooling.
Yeah. And the thing is that
these are data centers
the best way to dump heat, and this is the way, air conditioners, other things, is you just take your energy and you compress it and you get it really hot so you can radiate it really quickly. So the hotter you get something, the easier it is to dump it. And it's just a question of how much you can do it. And for the HSS, for the IS, you want to keep the mass down. So we don't want to have these compressors and all these other things we're going to run. So there's some mass penalties and reasons why you'd like to be able to do it without having to bring it. I don't want to have to bring a turbine in or something like that. That's why we use solar power in space, because we don't want to have to lug a big steam turbine up there to be able to produce things. So it's the same thing with theirs, that more than likely you can still do conductive heat transfer or convective heat transfer. You just have fluids that are going around whatever it is that you want to cool, and you run them through there, and then that heat goes out somewhere. But now at that point, we have to use radiative heat transfer. We can't use conveniently the river that we're next to or the ocean that we're next to take in that water for cooling and doing all this other stuff, or just blowing air over it. So it gets a little bit tricky, but I still think you can take whatever it is that's generating the heat, pull that heat out, then your working fluid, just heat the hell out of that, get it really hot, because we're going to the T to the fourth here, and then you'll be able to dump it. So again, it's an engineering problem. And it is, it appears to be very challenging, but there are ways to be able to do it. We do that all the time. If you look at a jet engine, there's no way a jet engine should work. Its operating temperature is way too hot. It's way above the melting point of everything in there. And 50 years ago, people said there's no way you could run, let alone one on a commercial jet
that's
at
thanks
those
to the
temperatures.
cooling on the
Absolutely
fins,
no
right?
way. Yeah.
The
So
coating material.
So in support of what Scott's saying, I would make the following proposal, and that is that these large solar arrays that we're building that are tidally locked to the sun or sun synchronous, so they're hot on one side, that the back is a radiator.
Yeah.
And that secondarily we explore looking at, ammonia as a refrigerant, the same thing that they do on the ISS, which literally lets you cool the chips and do the same sorts of things you might do on Earth with water. So, that's where I think ultimately, if you're trying to build these massive solar arrays that can become Dyson swarms, that's how you have to build it. The backside, the dark side, is the radiant side, and use all the area of the solar array to give you maximal surface area.
Yeah, and I agree. That's what you would want to do. And at the same time, solar arrays like to be cool. So if you can actually build in like cooling for the solar arrays at the same time, that would be a plus.
Yeah. Are you guys familiar with the idea of a Matryoshka brain?
Yes. The Jupiter brain. Yeah.
Yeah. Basically, the idea is if you look at a star at the center, and you do the first Dyson sphere around it at a certain distance, then to Scott's point about drop in temperature, you use Carnot's law and you do another sphere outside of that, and every one of them is compute driven. It's computronium based all the way down. So ultimately you could build a series of nested Dyson spheres that have, let's say, double the distance of each sphere, and then they'd get 1/4 of the energy to extract from the overall system.
Gustav, do you need to head off? Do you need to say anything before we head off? Yeah.
No, great chat. Have a family calling and need to go up and do the rounds tomorrow. So lovely seeing you guys.
We have to talk about Optimus on the moon and Mars, Gustav.
Oh yeah, that would be awesome. But I'll catch up.
So let me summarize some points here. Is that
let's just go back to Brian, your slides.
Yeah. Well, here's why I'm saying that the main point of this slide. So go ahead and go to that slide. The main point of this slide is this is what StarCloud was analyzing in terms of matching the ground-based, right? So I would make an adjustment here in that instead of saying 167 million for 40 megawatts, they have a 10-year assumption that you can use your chips and everything for 10 years. I think if they at least cut that down to 5 years. So basically getting to $80 million or less lets you match a 4 cents per kilowatt hour air facility on the ground. They have assumptions on the right for space, which I don't think are correct either. In terms of, but it's more towards an aspirational level. The reason I don't like their space-based one on the right, the second thing row down, they talk about launch being $5 million. So yes, SpaceX Starship can get down to that cost. They'll probably start 10 million and get down to 5 with full reusability based on 10 reuses, 20 reuses, whatever. You can get there. They will not give that price to everyone else, okay, for many, many years, okay? Right now, it costs them about $15 million to launch a Falcon 9, which is 1/5 to 1/10 the mass of the Starship. And then they charge $70 million for someone else to buy it, okay? Buying a launch, okay? So if they go down to 5 million for something 10 times better, they probably will still charge $80 million plus. So, but in terms of getting this back to near term, you can skip that slide, is that the V3 and that component architecture for the heating and all that stuff, there's a bunch of solved problems in the V2 and the V3. The V2 solves getting under $1 million per satellite, probably at $500,000 to $750,000 per satellite at the 20 kilowatt level. That has solar coming in and that has radiating the power. I'm bringing 20 kilowatts in. If I'm using for chips, I'm using for anything else, I'm radiating that heat away. And so they already have that 20 kilowatt thing solved at low cost. The V3 will have 2, maybe more AMD Versal chips in there. You don't have to go through the slides. AMD, this is just discuss redundancy for that. So this had the V3 being bigger than the V2, right? So that's the one on the left. So the V3, they already have designed. They're going to launch it next year early, right? Or start the first few launching probably by mid-year. and then they'll start launching maybe a few hundred, a few thousand by the end of the year. So they have the production lines ready to go on this V3. It has AMD Versal chips in there. AMD Versal chips, the amount we're estimating is maybe a couple hundred teraops, maybe 1,000 or so, based on how many they may have in there. So a pretty good chip, maybe combined in the H100 level range. So they already are doing a lot of it. They're just going to scale up with more chips and to figure out how much they can push it, how they have to adjust those chips, if they have to at all. Ideally, they're going to say, we don't want to adjust it all. We want to put some shielding, some other stuff on it. And then also for the scaling of the cooling, if they can get why do they don't build this giant structure? Is that they just want to make 1 million of those other things that they're already going to make 50,000 of, that they can adjust to do what they need to do as being holders and powering of chips, right? So it's more basic of not to the ideal performance, so long as it works and economically they can do it. So they can light up the chips, because even the existing production of Samsung and TSMC chips, this is StarCloud 2, that they want to make 100 chip structure, the other company, which is back, also has alliance with NVIDIA, that even the TSMC production lines, Fab 21, the other fab they're making in Taiwan, they have like 20 some things there, and the scaling of the facilities in Arizona and Texas, already that is too many chips for us to power. Okay, that's why there's all this race to get energy. I've looked a lot at all the nuclear fission companies, mass production. That will not close the loop before 2040 and beyond. You have to make thousands of those reactors. So if we can make new versions of giant solar factories, solar panel factories, that are space rated, and we already we'll have 5 gigawatts of capacity for what SpaceX needs for V3 already for communications, them going up 20x to 100 gigawatts for AI versions for the 1 million satellites. That's basically the next step, going from 9,000 V2s and V1.5s that were already up in space powered, to 50,000 V3s, to 1 million AI V3/V4s, and then shoving that up there and just making new factories that just basically make solar that's adapted to putting up in space, because that new solar in that orbit, and this is the structures of one of the tinier wings of a this is one they put up on the ISS, only slightly bigger than the ones they can stick on the V3, 2 sides of it. So that's just one side, and it's rolling out, so they have the deployment of it. So taking these technologies that work, slightly tweaking them and improving them, but just getting them at scale to suck up and power all these chips. And then whatever radiation cooling thing we have working now, use that. There are papers discussing what Chris talked about, the dual-sided solar and other side, and other heat loop things. Great to keep improving, not needed to power the first 1 million chips, the first 100 gigawatts. Because it's that race of like good enough powering, because 100 gigawatts of distributed chips is better than 50 million chips that are dead, not powered, right? Powered chips in space, unpowered chips sitting on the ground, or production that I can't use, right? So it's just, is there any other way to power it? If not, which is what I think Jeff Bezos, Google, and everyone's come to realize, is I can't power it any other way, right? So then I got to get in line. I'll pay SpaceX the tax to get it up there, because I can't power my chips any other way, because I've already used up my natural gas. They'll already be powering other data centers. My nuclear is still a ways away. Here is not base load power, where it's constantly working. Up there, in the right spot, as Chris says, it's base load power. I don't have to stick batteries on it. I don't have to do a bunch of other stuff. Each of those solar panels will be working 97% of the time. So that's the way to make lots, the 10 gigawatts, 100 gigawatts of base load power to power those chips. So it's far simpler than optimizing. It's just like there's no other way for me to make a power thing that's going to power up 100 gigawatts or a terawatt. This was the fastest solution. And recall that a terawatt is twice the base load power of the United States. The base load 100% on power is 500 gigawatts in the United States. Going to a terawatt is double the United States. So, and I can, by just taking what we can already make on the ground and then making it and shoving it into a super cheap launch, which is what Starship will be, is how they get there. And then the details around how many launch towers, how many Starships launches, how many flights and stuff need to happen. But so that's the actual roll-up timeline. But it's a lit up powered chips or not powered chips is the thing. So sorry for going on my little rant there, but that's
Actually,
No,
Brian, that was really good because in a way, what you're describing is the spec for the V4 Starlink
right.
has n number of chips. So let's say it's a 5x more solar, so it's
Yeah.
around 100 kilowatts. And then, as we've discussed, assume you could handle up to 100 AI5 chips or whatever the case is.
Yeah.
When I was discussing it earlier, giving it to Starlink to manufacture and basically treating that as a discrete SKU means you get the benefits of Wright's law at the same time on the technology that they're already using with solar and communications. And so that whole improvement life cycle for data centers comes under the Starlink banner. And,
Yeah.
you know, the gigafactory they've built there, right? So this is where I'm thinking it keeps the costs continually going lower. And that is not just the chips, but the solar, which is the limiting factor.
Yeah. Joel
Chris,
Sapp asked in
hang on,
communication about
Chris, just a little note. I think your green screen, or just can you just focus your camera a bit, please? Because you're kind of
Yeah, I see. I'm getting fuzzy, and I have no idea
Yeah,
what's
yeah.
going on here.
Yeah.
fuzzy logic is
So-
a bit outdated.
Yeah, so
There
Joel
you go.
Sapp, one of the commenters asked, Leo or sun synchronous. And so it is the sun synchronous that we're talking about, right? So that's a higher orbit. So some of the modifications with sun synchronous versus Leo, especially the lower, really low altitude that the V3 communication satellites are, is even less atmosphere. So then you can make it less rigid. So I can go lighter on the solar. That's a difference going up to sun synchronous. That makes it even lighter and easier to put power. And so that the three different types of satellites that they will have, they have the high-speed internet version, and then they have the direct-to-cell phone version, and then they have the AI version. Each one will be distinct. I won't overlap with a bunch of stuff because each one needs to be optimized for the orbit it's going to go to and for the power and other purposes it'll go to. So right now, the DTC, the direct-to-cell phone, and the high-speed internet, they're in different locations, right? One's higher, the high-speed internet, versus the cell phone, because you want to get as close as possible for lower latency and faster communication speeds for the DTC. And then up above will be a version of the AI versions at that location. The other thing was that Elon talked about in a post 100 terawatts from the moon, right? So briefly, that goes to the concept of the L5 O'Neill Society stuff from the 70s when everyone was really optimistic about Apollo, that if you mine on the moon, that you can lower the cost of putting stuff into high Earth orbit by about 10 times, right? So then so the 100 terawatts from the moon presupposes massive amounts of mining, massive industrialization of the moon in order to support that. But that basically means you would need to fully construct your satellite on the moon, because if I'm doing all this stuff on the moon and I'm still making chips and launching the chips from the Earth, I haven't really lowered my costs, right? So that means another reason that Elon's going to learn to make fabs, starting with the fab partnership with Samsung that they already have announced, and the fab partnership with TSMC, going to his own independent fabs on the ground, will then lead to fabs on the moon and fabs on Mars as he moves a reduced supply chain to the critical only supply chain over to the moon and then to Mars. I think that the beyond terawatt, the trillion ship location will be Mars. It won't be Earth orbit. It'll be Mars. Even though there's a reduction in solar, 40% versus closer in, that reduction is fine because I can build factories for bots, for mining, for also there's water for cooling there. So I can more easily scale and get a dense cluster, although diffuse power onto that, so I can power a trillion ships on Mars. And the other thing is, to Chris's point about singularity and all this stuff scaling, is that this $1 trillion plus that's going to go to scaling all the space-based stuff in orbit and then building infrastructure on the moon and Mars is the cost economics that enable us to industrialize the solar system. That we get over the hump of, well, everything's great once we get past this point and can build factories everywhere and all. This is what gets us there. That we will
I have a
to.
question here.
Sure.
And I want Marshall's input on this, because I want to also bring to focus and bring to light the geopolitics that is kind of forcing, in some ways, American companies, whether it's Google or Tesla or anyone else, Amazon, to go this route. Because, Marshall, you're pretty familiar with the problems that with the legal hurdles, the environmental concerns, all of those problems that AI scalers, data scalers have to deal with in America. They don't have that problem in China,
Nope.
right?
And Middle Kingdom's got lots of power, right? Lots.
Yeah.
Like Brian said, 80% of solar panels, and they have nuclear design down to a science, right? I literally just read a post on LinkedIn and we're talking about building nuclear is a one-off. Everybody's building a one-off custom cookie in the United States, and China just built one design and they just keep building them. And my joke is, let's just have China build them and put them on a ship. We'll pull it up to Virginia Beach, we'll cable it, and we'll power. Off we go, right?
Yeah, but it's ironic that the geopolitics are kind of an enabling factor to this. I have another question with regards. So we talked about solar in space. We've seen what's happened with the Shenzhou. Is it the capsule, the Chinese capsule at the Tiangong station was hit by orbital debris on the 5th of November. The return has been delayed. How big of a problem or a threat is this to all of these satellite-based data centers in space?
I'm going to throw my complete amateur, I'm not a space expert in any way whatsoever. Given that we already have lasers that can, shoot power and data, well, guess what? This goes back to the 1980s Star Wars, Ronald Reagan, Star Wars initiative, right? What's stopping us from coming up with, whether it's a laser or some kind of device to shoot at debris that comes at it out in space?
I have a different perspective. I look at it like pre-plan the damage. So if you're just looking at solar arrays, because that's the largest area, build your cells so that there's redundancy at the cell level, so that you can block things out, that there's error correction mechanisms or other ways of reconfiguring the satellite, the array once it's in place. And then this also leads to the second notion of not creating a megastructure in a fixed location, but instead just saying, if I have 1 million smaller satellites that are collecting their own, I have systemic ultra redundancy. If any specific node goes down, it's replaceable, just like Starlink's plan to deorbit X number over time. We need to do the same thing with both energy and intelligence. To say, oh, this chip array, it's old tech, it's 5 years old, just deorbit the whole thing.
And that's what Starlink has been doing. They've launched nearly 11,000 and they deorbited 2,000. Anything that wasn't quite right, they did, instead of bothering to fix it or trying to work around some problem, just get rid of it. We'll just launch some more in 2 days. So they're not keeping stuff up there. And for the debris problem, if they had a major breakup of a satellite, it's less of a problem for the DTCs, direct to cell phone, because they're so low that anything that breaks up there would deorbit itself in like a month or two or something, 2 months, something like that, because it's so low. And they keep going lower, it's easier. At the higher altitude, if something breaks up, then that'd be a problem. There are companies working on space debris problems. You can use lasers and other solutions to try and clean up debris. If you have abundant starships, you could have a starship system, that unfurls some kind of netting thing to kind of like, scoop up. It's like taking some kind of like filter thing through a bunch of, your soup or something like that to like scoop out little chunks of whatever you don't want to be in there. So there are ways to do that.
Yeah.
So
I think this
it
guy
wouldn't
has
vaporize
an
debris.
interesting comment.
Yeah.
Laser doesn't vaporize debris to nothing.
You wouldn't vaporize it. You'd be putting pressure on it to like force it down. You're kind of like shoving it away and getting it lower and lower until the gravity takes it away. You're not destroying it. You're just like kind of trying to sweep it down lower. Is your action? You're trying to like.
So here's
increase the
another thought. We've been talking about the energy basket, and there seems to be a kind of a overemphasis on solar. We have thorium on the moon. We know the Chinese are looking at exploiting that. Have you thought about the possibility of maybe small modular reactors with thorium on the moon to add to
So
the energy
the
basket?
problem, all these things is those would all work. I've talked to the companies, 30, 40 companies. It's all fine. The first of a kind reactor for a small version, like teeny tiny, like 100 kilowatts, 1 megawatt, they get some of those working maybe next year, 2 years, or whatever, right? But then anyone who's going to make like 10 megawatts, 100 megawatts, 500 megawatts, it's going to take time, like 2030, 2035, to make your first of a kind, and then I have to mass produce them. So then I have 10 years at least before I can start making 20 gigawatts or 40 gigawatts from that. And the old technology, the most I can push it is to get another 10, 20 gigawatts, right? It's just not enough in time because I'll need to light up 1 billion chips in the 2030s, right? Maybe 2 billion chips in the 2030s. So I have 2 terawatts I need to light up. So if my nuclear, and also for thorium, I got to do a new fuel cycle, right? So that involves a bunch of mining, a bunch of other stuff. So anything that involves that takes 2 decades to get to something serious, right? So in the meantime, how do I light up all those things? And that goes to solar, doing batteries to try and increase the thing, the grid efficiency. But that also involves, like when Elon says, I'm going to make all these batteries and can double up the power that we generate in the United States, right? That still involves some amount of grid. That still involves increasing coal and natural gas production and uranium production so that can power existing plants, right? So there's a bunch of logistical supply chain things to do it. So we know we can make a terawatt of solar. We're already doing it. Now we just say make a terawatt of solar for space and launch it. So that's the argument there. And even if it doesn't become the full solution, although potentially it looks like it could be, then at least the every gigawatt that you do is worth $20 billion, $50 billion or more to the company that does it. So in terms of like the Tesla shareholders, SpaceX shareholders, if they do 100 gigawatts, that is worth $2 trillion, right? So that pays off my $100 billion for a fab, right? So
Rodney, can I add a little bit to this? Because I think we might be asking the wrong question. So, when we're talking about alternative energy sources, we forget a couple of things. One, the sun is the only scalable and continuous energy source. And I say that again because we discussed it before, and introduce Tony Seba and Rethink X and their book Stellar Worlds, and Tony Seba's long discussion that says, hey, we are at the point where solar's like a penny a kilowatt kind of thing, or a penny a watt. So from purely an economic, the ability to, as Brian says, build the machine that generates a terawatt of output It's far cheaper to do solar, regardless of whether it's terrestrial or space-based. And the fact that this is already mature technology means that we're at the bottom of the cost curves and we're going to get the most bang for the buck. And it's also deployable today. We don't have to wait for some time in the future. And then to circle this back to what Brian was discussing before with the O'Neill thinking in the 70s with the idea of ISRO on the moon and regolith and all of this, I think that that whole approach is misguided, giving Starship offering, $10 a kilo ultimate launch costs, and that what this really means is that you need to say, where in the universe do I already have a chip fab? Where is it that I have all of these things that I can build the stuff and then use the low cost to orbit to let Starship just put it there, whatever it is. So, well, in theory, you'd say, well, maybe I want to make chips in space, and there might be a case for that when compared to a $50 billion fab that you have to worry about earthquakes. And, there could be a case for building chips in space. But on the short term, leveraging Earth's ability to produce finished goods that then is just moved into space as a satellite, as a complete product, is the fastest way to get our economic engine to get the maximum number of things in space for the lowest cost, and the way to leverage Wright's law.
Yeah, I want to. That's a perfect segue to something I want to broaden out in this discussion, which is the geopolitics of it, right? And I want to harken back to the spat between Elon and Sean Duffy when he was NASA administrator. Elon's decision and announcement to say that he's going to go and build Moonbase Alpha essentially on his own. Now, this has implications for geopolitics, right, and the space race between the US and China. How do you see that playing out with a private entity like SpaceX/Tesla? Because right now, space is literally the wild, wild west. You have the outer space treaties, you've got the Artemis Accords, but essentially boils down to how do you stop someone who has the wherewithal and the capability, the willingness, and the funds to just build a Moonbase Alpha, who has a near monopoly, for all means and purposes, on Mars to orbit, the rocket that takes it to space, all the technologies needed, the AI, the bots, everything, to just set up a space economy anywhere, whether it's in orbit, on the moon, or Mars. What are your thoughts on how this complicates the space race and geopolitics?
They got to launch from somewhere. That's the thing, is you don't give them a launch license, or you don't.
Launch from water, Scott.
Well,
they launch from water on the starport now.
Yes, but water. But the thing is, water requires resources. The resources have to come from somewhere. So you could easily interdict. So if some government was like, no, we're not going to let this private person, this Bond villain or something like that, you imagine out in the middle of nowhere, stuff comes from some. I mean, you need people, you need resources. Things have to be mined. Yes, there's a lot of black market and stuff like that, but I'm just not sure that someone could do it. And the UN will be sitting there pounding their gavel and writing all sorts of strongly worded letters that he shouldn't do this. But in the end, you're going to require some sort of cooperation between other corporations, and I don't know how much you can do that through piracy or something like that, or through third world countries or something like that wouldn't want to go in there. So it seems like if they really wanted to, they don't have to go to the moon to stop them from doing that. They just got to make sure you can't get off the Earth.
Yeah. I mean,
well, that's
at
also
the end
what
of the day,
cosmic filter's for, right?
Yeah.
Yeah.
Okay, but
once you're there, I mean, once you've established the presence, and if you're able to do it there, no one's going to stop you unless they come up and say.
No, but I want to push back on that a bit, because even though there are these loopholes that exist in space treaties and laws, the fact of the matter is that the U.S. government is still responsible under all these treaties for whatever SpaceX does. Mm-hmm. And at the end of the day, you cannot wish away geopolitics on Earth. So
they can just say, "Oh, we changed our mind," and and who's going to stop them then? So the main thing is, at some point you would need a substantially large country to give you the blessing to that individual to go ahead and do it, and you say, exactly. You can go ahead and do whatever you want. It would be very hard to not have some sort of cooperation.
Brian, do you think that's what's brought about the realignment between Trump and Elon? reality?
Well, no, they're friends, and then Elon, the important he's building stuff. It is why make him an enemy? That was the mistake that the previous administration made, where they
Yeah.
said, "Let's make him an enemy for no good reason." Right? He's delivering stuff, just like Jensen's delivering stuff. There's no reason to say just because I'm worried, I'm going to make you an enemy. You always have top companies. You have Microsoft, you have Google, Apple. There's no reason to make any of the companies enemies if they're like delivering value to the world and to your country. And then for the historical example of a company that was basically controlling a whole territory, you have the East India Company back in the day, which was controlling large swaths of North America, right? So that was a highly profitable company that was one developing all that. So then how much did did England have control over what the East India Company did over North America? And then ultimately, all that stuff that East India Company did in North America became the United States, Canada, etc. So then those things broke off. So with the history that happened there, I think ultimately that's what will happen. Like as the economies of orbit, Moon, and Mars become roughly equivalent to beyond the 13 colonies, 2 million people, they'll demand their own rights, right? And then there'll be some breakup there. There's no reason that the countries in and the governmental control that's in Earth should control that. So that's where it will eventually head. In the meantime, what Scott said is correct, that you control the people who are here, just like China could control Bitcoin by knowing where the miners were generating their electricity because they had to suck so much power out, and they can say, okay, now you must follow my rules, got a gun to your head or whatever. It's like there's still people and they're still doing stuff and there's still control, but ultimately that shouldn't be what you should be doing. That the reason the U.S. has certain growth is because they have a laissez-faire thing, more of like let you do what you want, versus how much did Xi Jinping kneecap China by saying, I'm scared of Alibaba, I'm scared of Jack Ma, right? And so I'm going to control them and then prevent the tech companies from going. So then now the top 20, top 30, I think only Tencent is in the top 20, right? And all the rest got down. And China's level of growth and innovation, I think, got hampered by that level of, I'm worried about what you tech guys are doing, right?
Yeah. Marshall, you were making a point, sorry.
No worries. Really, just comic, right? So until extraterrestrial, also known as little green men Martians, show up and say, no, you can't be doing this, right? Or maybe not little green Martian, right?
Yeah.
Royden, if I can add to this, especially when it comes from the perspective of the singularity, one of the things that we discussed with people is there's a reasonable probability that 40% of all nation states will not exist by 2040 due to the disruption.
Stop!
Of
You're
the
scaring me.
But that's exactly the point. So then, when you try and frame this in geopolitical terms, you say, look around to the nations that are going crazy, let's say, or they're doing bad ideologies, or they're having problems with their economies.
Well, look at America. Look at Canada.
Pick your nation and pick your reason.
Yeah.
But the point is probably that most nations are going to collapse due to social, ideological, adaptive problems because people just can't handle the pace of change, or we're just going one step too far. So we see the back and forth where some people are trying to be more grounded, but what I see is the likelihood that the US with Musk is being positioned as the supernation that becomes the world government on Earth. And that this will likely happen over the next 5 years, whether anyone else likes it or not.
What about Mars?
And to your, morals is a separate conversation because
Mars.
Oh, Mars. Well, I'm actually talking purely terrestrial because I think that's all that matters, right? Is that as we look at these various countries collapsing and others ascending, some of them with space technology, let's assume it's US and China are the two that are going to survive, then, the ability for those nations to be prosperous and to have global dominance is one factor. But the flip side to what you were inferring earlier was that we need to get the permission of our emperor, lord, nation states in order to do something. And this is where we tie over to abundance and the shift in our minds and mentality. And what Peter talks about is being in a permissionless, abundant society. I don't need to ask a politician if I'm allowed to do this, that, or the other. And this also ties into the stellar worlds and the idea that Tony Seba and Rethink X are talking about, is when you get rid of the extractive system that requires the citizen to become a cog in the machinery of capitalism and to follow the social rules and norms, then you're invariably going to have a populace that has given up their freedom, their decentralization, their rights, their independence. And that's where I'm advocating for things like micronations as these individual nations fail, that would be more abundance oriented and use exponential technologies to build the abundance community, believing that, I don't know if you guys are familiar with Arthur C. Clarke's Childhood's End. It's my favorite book. But basically, it's a story about aliens come to Earth and say, we give you everything. We give you a perfect economy, no disease, no illness, no anything. And the humans go, screw you, fuck off. Right? And Arthur Clarke wrote this in 1953. And it turns out that, just to spoil the old story, the overlords have come to Earth in order to find the few number of humans that are going to be smart enough to ascend into the cosmic community. And the rest of all adults will just get to live out their natural existence. So circling back to our original point, I think we're a little bit thinking like humans do, and that, we're not in a transitional phase of shifting to a mechano-organic life form that is not going to be bound by any nation state. And if you want to look at how billionaires today get control over their assets and they can do what they want, and ostensibly that's what you're saying, the world's first trillionaire gets to build whatever colonies on whatever planet he feels like, and even the US government is not going to be able to stop him because the only master he knows is the laws of physics.
Yeah, you've got a very valid point there.
Yeah.
The implications are scary, immense, profound, and scary. And then I think that really boils down to what repercussions that brings about in American society, where you right now have a clash between Republicans and Democrats. Already you've got people saying Elon is too rich by far, and so they're going to try and bring about some sort of a structure to control him. I don't know if it's, I mean, it is plausible, it is possible, but I don't know if the path to that is going to be as smooth politically and socially in America, let alone elsewhere. I don't know.
Well,
Okay.
I think for me, one of the big questions, Roden, and you and I have talked about this before, is as individuals, how do we use the age of ASI to personally put us into a place of abundance? Ourselves, our families, our communities, those people that we care about, realizing that maybe 5% or less of the population could enjoy this vision of abundance, while 95% is going to mess it up in the execution. So the key is how to be part of the groups and the people and the conversations we're having, like-minded folks, to say, hey, I want to build this kind of future, and I'm not going to get bound into human idiosyncrasies and rules and laws and nation states, and because that's partly what I'm asserting is a process that every individual has to go through, which is to shed off that which is human, which doesn't serve you when you become transhuman, whatever that ends up being. That's a personal journey, right?
Mm-hmm.
So I'll leave it there.
That's a futuristic way to end this podcast. Thank you so much, gentlemen. It's been wonderful. Brian, Chris, Marshall, Scott, Gustav, And of course, Meherda, thank you very much. It's been a pleasure chatting with you, picking your brain, so much to learn. You guys have taken us, me and my audience, to school, and we always love it. Till next time, thank you so much.
Thank you.